Hello.
Yes, Dheeraj sir, we can start now.
Hello, hello.
Uh,
Yes, sir.
Hello.
Yes, sir. Yes, sir.
Am I audible?
Yes, sir.
Yes,
You are
yes, yes.
audible.
Very good morning to all. Once again, we are going to start our new session of the day 5th. I welcome all the participants and esteemed guests. Now we begin with our first technical session of the FDP. It is an absolute honor to invite our esteemed speaker, Dr. Rajan Agrahari. He received his PhD degree. He received his PhD degree from the Indian Institute of Technology (BHU) Varanasi in the field of microwave engineering in 2019. He has worked as a postdoc fellow at the International Research Center for Nanophotonics and Metamaterials, ITMO University, St. Petersburg, Russia in 2020. He was also the adjunct research assistant at Pennsylvania State University, USA in 2017. Since 2020, he is associated with National Institute of Technology, Patna, Bihar, India. His area of research includes nanophotonics, computational electromagnetics, and metamaterials. He has been conferred with the IEEE MTTS Outstanding Chapter Officer Award 2024 in 2010. He is a member of IEEE and life senior member of the WAMS Society. We are privileged to have him with us to speak on the topic metamaterials-based biosensors for biomedical applications. So I request Dr. Rajanagarari to please take the session.
Thank you so much for the very nice introduction. Before going to start, I would like to thank the organizer, especially UNES and from the MNIT Allahabad and from Galgotia University also. Since this workshop is organized by both the university, Allahabad, MNIT Allahabad and Galgotia University, and it seems that the topic is very trendy and very interesting to the participant. That is why the huge number of participants I can take. So before uh, not wasting the time, let's just let me share my screen. Let me share my screen. Share screen. I got it. Just confirm please that my screen is visible to everyone.
Yes, sir, yes, sir. Put it in full screen mode, sir.
Okay.
Yes, sir. Go ahead with your presentation.
So the purpose of today's just talk is to motivate you because I'm going to just give you the brief of the metamaterial based sensor for biomedical application. What actually metamaterial can do in sensing and especially in the biomedical sensing area, and by incorporating the periodicity or the metamaterial, how we can actually reduce the complexity of the structure, how we can reduce the size of the sensor. So these are the very interesting things that you should know, and I will not going to bore you all just showing the complex questions of electromagnetics or something so that you can go. I just my purpose is to motivate you to all towards this topic, and if any of one of you are motivated towards this topic, then it will be a great achievement for me to towards if you are interested in this topic to work in your future. Okay, so let's start with this topic, metamaterial based sensor for the biomedical application. So, of course, what is a metamaterial? Since the sensor which we design, it totally depend on the behavior of the electromagnetic wave, how the electromagnetic wave uh, operate or its response in the sensor that we will study in the sensing device. So, before going to study the sensor, let's just take the brief view of how the electromagnetic wave are propagating, what are the actually electromagnetic wave, and what are the basic principle of designing that sensor. Okay, it is something like if you are not from the electronics background or not from the microwave background, it is something like you have X-rays and infrared rays, similar like that. The microwave reason we have electromagnetic wave, and the wave. What is wave? Actually, wave is nothing but it is a uh, we can say that it is something which transport the energy. That the wave, it can be any type of wave. It can be of sound wave, it can be of light wave, it can be EM wave, it can be of water wave or whatever. If you think that the wave something which transport the energy, whatever I have shown here, it is showing the simple electromagnetic wave, electric field and magnetic field, and the direction of propagation. Where we can see that the electric field of the electric field direction in the y direction, magnetic field in the z direction, and it is propagating in the x direction. This is called the transfer electromagnetic wave. This equation shows this equation shows the wave equation which comes from the Maxwell equation. You must have studied in the physics. And what actually in the practical scenario, we study the plane wave. We study the plane wave. Plane wave means what is the plane wave? In the real scenario, like you have a torch, and at the far field, at after the some distance, when you see the light gets spread, and you will see that after the some distance, that light have become its phase become constant. But that light at that distance is we can say that it is similar to the plane wave. But in the real scenario, you can just take a dipole antenna. It is a dipole antenna, and when it transmit the electromagnetic wave at the far field, this is called far field. Far field means the distance at some there are some distance from the dipole antenna. Generally, it is 2d square by lambda. So at the far field, you can see that this is wave. This wave is called the plane wave because in the plane wave, at the constant plate, the phase is constant. At a certain field, the phase is constant. That type of wave is called the plane wave. So in the real scenario, actually, we take this plane wave for the any analysis. So let's just see how the electromagnetic wave propagate in the different area. Like you have a plane wave, and there is a air. It is a air brick I am showing here. But let's suppose this is some similar. Just it is air only. So in the air, you can see that electromagnetic wave transmitted smoothly. There is no transmission. There is no reflection and scattering. You can say that. But in the next case where the plane wave is incident on the dielectric sphere, so if there's a air as well as dielectric sphere, so you can find that the electromagnetic wave which incident on this computational domain, you will find that the transmission, there is a scattering of the wave you can easily find. And why this has happened? This is just because of the discontinuity in the permittivity, because in the first case there is no discontinuity of the permittivity because everywhere there is a air. Epsilon permittivity will epsilon is 1, but in this case there is a discontinuity in the material property, like either here epsilon is 1 as well as epsilon of there are some epsilon for the dielectric sphere. So due to this epsilon discontinuity, the scattering of behavior you can observe. Okay. Similar to the take the next example. This is a different type of wave, surface plasma positron wave, SPP wave, which propagate at the metal and dielectric interface. I will show you the two different cases. The last slide, I discussed the discontinuity in the material. In this slide, I'll
Rajan sir, Rajan sir.
Yes, now I'm
In
audible.
between, actually, it seems it got disconnected.
I know, I know.
Okay.
Power due to power cut. Now it is, I think.
Okay. Okay, sir. Okay, sir. We can see you do full screen and you can.
Yeah. Okay, so in the last slide, actually, I just show you the discontinuity in the material. In this slide, I'll show you what actually happened when the discontinuity in the structure happens. Discontinuity in the structure means here you can see the metal. Below this pink line is the metal material, and above it is a air. Okay, and this metal brick is continuous, but suddenly there is a metal discontinuity or structure discontinuity, and then again metal. This is one case. Another case is that metal is not the continuously brick. It has some concave corner, or this is a metal side. So we'll see one by one. So this is a surface wave. Surface wave is the wave which propagate at the surface of a two different material. Here, the two different materials are metal and dielectric. The bottom one is metal and the above one is dielectric. So let's see what happens. So you can see that as it is surface wave, most of the wave will be in the air only, and in the metallic side, there will be very small strength, and it is very beautifully propagating the forward direction till it encounters a discontinuity here. Due to this discontinuity, what you find that you can see a very small deflection in the that surface wave, and the most of the wave go in the forward direction. So what actually happening is that due to discontinuity of this metal, you are actually disturbing the wave behavior. Similarly, in this case also, the second one where there is a concave corner, you can see here the surface wave launch from this structure, then again it encounters a discontinuity because it is not no more a plane. It will be a concave corner. As it is a concave corner, surface discontinuity occur. There is a reflection and transmission you can observe. So what actually you can see here that due to the geometrical asymmetry, you can actually change the property of the electromagnetic wave. So from last two slides, the first slide and second slide, what you can conclude that we can actually manipulate the electromagnetic wave, light wave or any wave, okay, by changing the permittivity of the material or medium, or you can also change you can also manipulate it by changing the structure geometry. That actually my point from last two slides. You can actually alter tailor the property of the EM wave by changing the material discontinuity or by changing the material, or you can also change the property of the material that EM wave by changing some structure geometry. So let's come to this point. Now coming to the last slide, I have shown just very simple example, dielectric sphere and surface discontinuity. Now you have some kind of a periodicity in your structure. Like you can see here, this is a dielectric cylinder which is arranged periodically in some manner. In this example, it is arranged in the square lattice. Okay, what actually happened? If you are aware with that, then it's good. But in the physics, what happens in the light frequency, in the visible light frequency, what happens when the light incident on this frequency, it passes certain wavelength gap. Means that let's suppose the wavelength of this incident wave. Let us suppose the wavelength of this incident wave is lambda 1, and this lambda 1 is smoothly passes through this geometry periodic structure and transmitted for propagated in the forward direction when the wavelength is lambda 1, but uh, okay, when the wavelength is lambda 1, but let us suppose I change the incident wavelength, make it lambda 2. Okay, so when lambda 2 is incident on it, what happens? Instead of propagating in the forward direction, it all the wave get reflected back. So why this happen? Just because of this periodic structure generate a band gap, which we call the photonic band gap. Band gap means that, let us suppose for an example, this photonic crystal is creating a band gap between 400 nanometer. I'm just taking the visual frequency to 500 nanometer. So what happened whenever the light which have a frequency or wavelength in this range 400 to 500 nanometer, all the wave will get reflected back, because this structure is designed such that, because this value depends on the radius of this dielectric cylinder, the gap between the two dielectric cylinder and the lattice what we have used. So this you can actually manipulate this 400 to 500. You can change it by changing the radius or the distance between that. So what actually happening that due to this periodicity, a band gap is created, which we call the photonic band gap. And when the wavelength of this band gap will incident on this structure, this will not propagate in the forward direction. It will all the way will reflected there. And this kind of structure is called the photonic crystal, which is a very famous term. Okay, and this happen when this phenomena happen at visible frequency or visible light frequency. Okay. So now what happens? The same concept you can duplicate in the microwave frequency at the lower frequency, and that at lower frequency we call it, because we call it metamaterial metasurface, or you can also call it frequency selective surface. Here what we do, we have some periodic structure, unit cell structure, which we periodically arrange in x direction as well as in y direction. So when you periodically arrange any structure, so actually what you are doing, when any wave is incident on it, you can control the polarization of the wave, phase of the wave, and amplitude of the wave. Overall, you can say that you actually are playing with the electromagnetic wave by just changing the geometry of the structure or material which you have used here. So this is what actually from last three slides I wanted to show that what is the basic principle of designing any structure. Okay. So this is the metamaterial. So what actually metamaterial is? So metamaterial is simply a kind of a periodic structure. You can see that this is a periodic structure in the three-dimensional x direction, y direction, as well as in z direction. So if you have a periodicity in the three direction, then that type of structure we can call it metamaterial. But of course, this type of structure fabrication is very complex. So we move to its two-dimensional counterpart, which we call it metasurface. Metasurface is nothing but it have a very thin surface, which means that the thickness is very small. The thickness of this material is very small, and there is a periodicity in the two-dimensional. Here you can see that in the example, the periodic. This is the unit cell structure, or you can also call it meta atom, which arrange in the x direction as well as in y direction. So this kind of two-dimensional periodicity, two-dimensional periodic structure is called the metasurface. And this unit cell structure usually have a length of lambda by 4, or we can call it subwavelength structure. Due to this subwavelength structure, you can actually effectively manipulate the electromagnetic wave which is incident on this structure. Okay, I will not waste your time. This metasurface is basically of two types: reflective type metasurface, transmitted type metasurface. Reflective type, as it is clear from the name, the device which only reflect the wave, there will no transmission. Then this type of structure is called the reflective type metasurface. These are the equation. I will not go to the detail. I don't want to bore you from this complex equation. But of course, just I am giving you brief. This equation is the incident wave, which is the plane wave equation, and this is the reflected wave equation. Due to this periodicity of this structure, we apply some Foucault bonding condition. Due to this Foucault bonding condition, we got this equation. Okay, and here the PQ and RXX, RY are the reflection coefficient. We call it co-polarized and cross-polarized reflection coefficients, and this alpha is the wave number. Similar to the reflective type, there is a transmittive type metasurface. Transmittive type metasurface means that the wave which transmitted, or most of the wave is transmitted in the forward direction. There will be very less reflection, or you can say that reflection is almost negligible, small. This type of structure is called the transmittive type metasurface. Okay, and If you wanted to calculate the absorption, then you can calculate it with this expression. Okay, this is some of the technical term, like in most of the cases we check about the TE and TM mode, specular mode and non-specular mode. Specular mode is something which is a X polarized and Y polarized way, and non-specular mode which is unwanted way, which we wanted to suppress, which we wanted to avoid. So actually, I'm showing here why we require L is less than lambda by 4. If we take L greater than lambda, what will happen? If you take L is greater than lambda, means this unit cell length is greater than lambda. In that case, uh, this is a non-specular mode started coming into the picture, but this is a not desired mode. This is not desired. We always wanted to suppress this mode. So that is why if you wanted to suppress this mode, you have to check that your L should be less than lambda by 4. Otherwise, if L is your greater than lambda, then this mode will come into the picture and your device will not effectively work as a sensor. This is the thing. So what are the applications of metal surface? Absorber, polarizer, beam shaping, sensing, lenses, holographic, clocking. There are many more applications of this. And in my lab at NIT Patna, we are working in almost all the areas. And I will today explain mostly in this area, sensing for sensing application. Why the meta surface, how we can use the meta surface for the sensing purpose. So let's see. This is our first example, terahertz biosensor based on the meta surface based terahertz biosensor for tuberculosis detection. How we can detect the tuberculosis by using this meta surface. So this is the paper which was done by our lab at NIT Patna and published at Tinano. So what actually we do, like I have shown in the earlier slides, that we are going to design a meta surface. So the new concept is here what most of the meta surface have a unit cell of a square unit cell, but in this case we have chosen non-square unit cell. Due to this non-square unit cell, this is a unit cell structure and this is the whole structure which is a periodic in x and y direction, and the thickness in z direction is very small. And above this structure, which is act as a sensor, will place a sample, like with the sample which you wanted to detect, you will place above this structure. Okay, so this is let's suppose first analyze the structure without any sample. We don't put any sample here, or you can say that there is a air or permittivity of the background permittivity is 1, means your sample or sensor is placed in air only. When this sample is placed on the air only, what will happen? When because the electromagnetic wave which incident on is, there are two type of electromagnetic wave, X polarized wave and the Y polarized wave, which I have shown in the last slide. That X polarized and Y polarized, you can understand it simply that a wave which have an electric field in the X direction called X polarized wave, the EM wave which have an electric field in the Y direction, which is called a Y polarized, in the simple manner. But if you go to the more deeper, so then you will understand that the linear polarized, circular polarized, and elliptical polarized. I'm not going to that detail. That will confuse you more. Just you can understand that X polarized and Y polarized means that electric field direction. Let us suppose this in this case, in electric field direction is Y direction. You can also have an electric field in the Y X direction also. Okay. So when if X polarized or Y polarized wave incident on it, the reflection is measured. The wave is incident on this, deflected back from this structure. We put a device, we call it vector network analyzer, VNA, and from that VNA we measure. Of course, before VNA we have an antenna which receive all the reflected wave from this structure. So this antenna receives some reflected wave from this, and this reflection coefficient you can see here. So the reflection coefficient for the X and Y polarized is shown here. Corresponding absorption is shown in this plot. Absorption is calculated from absorption is 1 minus reflection minus transmission here. This. Okay. So what is actually I wanted to show here, that the first peak is fine. This is a normal peak, like we just like happened in the normal peak. This is something which is due to some resonance phenomena. These peaks occur. This resonance is either the electric resonance or the magnetic resonance. Due to this resonance, this phenomena happens. The reflection is suddenly goes down, reflection is suddenly goes down, but the reflection is almost negligible. All the wave get reflect absorb here. So absorption can you see? You can see here. So if you look at the X polarized wave closely, X polarized wave have a two peaks, one and second peak, but the Y polarized wave have a one peak only. So you can see that for the Y-polarized wave, we are not interested because Y-polarized wave have a one peak only, but the X-polarized wave have a two peaks. And this X-polarized wave, second peak, this peak is very, very important. Why? Because this has a very narrow, very sharp peak, and the narrower response will give you the more narrower response will give you the more sensitive uh, device. So this due to this very narrow peak, this much very high quality factor sensor we have designed. This is a very very high value. This 574.46. Nowadays you will hardly find this hard this value, this much value of the quality factor. Okay. Now, how we will see that how it act as a sensor. So what we do initially, this behavior is for epsilon equals to a. Epsilon equals to a means when the background material is air. Now we change the background material from 1 to 1.02. This is although it is a very small, it is close to air, but we are changing very small permittivity. You can see that the resonance peak is shifted. This is a zoom version. So although there is a very small change in the permittivity, you can see a very large shift in the resonance peak. When the epsilon is air, then the peak is this. When the epsilon is 1.02, which is very small increment, the shift is very large. Similarly, 1.04, this again it is shifted, and you can see that from 1 to 1.1, it is shifted a very huge amount. So what actually this is showing that once this is showing that this this device is very very highly sensitive, a very high sensitive to the background refractive index. You are changing the refractive index, and this behavior is very sharply changing. Now, what is the reason behind this? This I'm here it is showing that the surface current plot for the two different frequency, like 1.92 terahertz and 2.7. You can see here, this one, the first peak is coming at 1.9 terahertz, the second one is coming at 2.7 terahertz. So just analyzing why this is happening. So 1.92 terahertz, this is showing the surface current. Surface current is the current which flow at the surface of the structure, which is basically it is come into the picture when there is a metal. Otherwise, it will not flow into the direct. 2.7 terahertz to 1.9. So 1.92, which act as a normal absorber, there is a no sensor. You can see that most of the electric field is concentrated towards this bow type of structure. But when you and there are also bow type of structure. But once you when you check the 2.70 terahertz, what you observe that the electric field is concentrated on the bow type structure as well as the whole surface. The color you can see that here the color at the remaining part is green, which is very narrow, very close to zero. But here color of the arrows are dark red. Dark red means that electric field intensity is very large at this whole surface. So what it is showing that this happens, this second peak, the second peak which I am showing that this is due to this surface resonance, and this surface resonance is very highly sensitive to the background refractive index. Okay. Okay. So this is actually I wanted to show that what is the reason behind those two resonances. Now coming to this here, which changes the background permittivity from 1 to 1.9 approx, and we can see that this is the color showing that absorption, and blue colors of course the red color means absorption is very high, blue color means absorption is almost zero, and here you can see that this absorption is also very high, this peak, this is very narrow. But the important point which is here to note that when you increase the permittivity, this peak is almost constant. The frequency is almost constant. Frequency is almost constant. But the second peak frequency is varying, which I was showing in this slide also. So frequency is varying. So what it is showing that up to 1 to 1.9, it is very effectively working as a sensor, and for very small change in the refractive index, the large change in the this resonance frequency can be observed. Okay. Now the sensing parameter is calculated. The sensing parameter means the sensitivity, a very high sensitivity of 2.34 terahertz per RIU is observed. A very high figure of merit of close to close to 450 it is observed, and the quality factor, as I saw, that 554 is very large, which was also observed. And this actually shows that at different frequency, as the refractive index increases, the quality factor also reduces, but the reduced value is also very high value. It is of more near around 400. And of course, as the refractive index increases, this figure of merit is also decreases, and sensitivity is also decreases. Now we tested this sensor for the tuberculosis. Okay, that design part is over. The tuberculosis, of course, it is not done on the practical. This is all the done. All the work was done on the simulation part only. So what happens? We have taken the different samples of tuberculosis. NBS means there is no type. There is no TB type. This is a normal blood cell. Okay, TB1 which are TB1 affected blood cells, TB2 with TB2 type of TB2 affected blood cell, TB3 and TB4 are different types of category of tuberculosis. Okay, so all the, because as you have a different TB tuberculosis, different category of tuberculosis, they all have a different refractive index of blood cells. You can see that for normal blood cell, it will have a 1.351 refractive index. For TB1, it is 1.348, very small change, 1.347, 1.345, and 1.343. As there is a TB categories increases, the refractive index also decreases. So we just, when we put this value on the background as a background refractive index, so you find that the shift in the resonance frequencies occur, and the quality factor for the each and every one is calculated. It is almost, it is near around the 410 for all the tuberculosis, and the sensitivity is around 1.5 terahertz for all the category, and the figure of merit is close to 300 for all the category of the tuberculosis. So which are the very high value. So, and you can also observe this in this diagram also, that when there is a normal blood cell, you can see that the red curve is given, but there's a TB1, TB2, TB3 as a background refractive index. The shift in the refractive index occur. The blue one is the TB1, green one is the TB2, light blue is the TB3 and TB4. So you can see that as the category, a different category of TB closest samples come, we have a different peaks. So from that shift in the peak, you can actually detect that whether there is a whether there is a, what we can say, tuberculosis or not, whether it is a normal blood sample or whether it is a tuberculosis sample. Okay, this sample have a this device, sorry, this sensor have a one limitation which we have designed here. The limitation is that the detection range of the detection permittivity detection range is very small. Means that it depends on the, but actually it depends on the quality factor, or there is a trade-off between the quality factor. There is a trade-off between the quality factor and the permittivity range. How? Like if you want high quality factor with high sensitive. So you can see that if you want very high sensitivity, 654, you can achieve very high sensitivity with our design, but that will reduce the detection rate. It will detect only 1.0 to 1.42 permittivity only. And again, you are coming to the this one, that once you want, okay, I wanted a large number of permittivity to detect. So that, like this one, you here in this design, you can detect up to 1 to 2.38, but in this case you have to compromise with the quality factor. So overall, there's a trade-off between the quality factor and permittivity rate. Means it depends on your practical application or at what permittivity you wanted to detect. So so if you want to large permittivity rate, then in that case, the quality factor will be small. But if you want a large quality factor, in that case, detection then will be large. How you can achieve this? By changing the dimension A. Dimension A means this one. Just you, if you change the dimension, then you can actually alter the property. So I'm telling it from the beginning of the first slide of my presentation that actually what we are doing. We are just changing the parameter of the structure or making some unsymmetry or making some disturbance, making some uh, discontinuity in the structure of permittivity, or we are tailoring. By doing that, we are tailoring or manipulating the electromagnetic wave. So what actually we are doing here, I'm just tailoring the structure geometry and tailoring the property of the electromagnetic wave. This is a very important, or we can say the very significant or very uh, beautiful behavior or property of this beta surface of periodic structure. So this is the limitation what I have said, that what just I have tell that detection range or large detection range is not possible with this sensor. So coming to the next, we try to design the another one design. This one is the another design which is again metal dielectric interface, and here in this case it is not the reflective type. This one is the reflective type, but a surface reflecting means all the wave will get reflected. But this one is wave will incident. But you have some horn antenna here, which incident the light, and from here the wave will transmit, and we will have some horn antenna here which receive here and connected with the VLF. So in the previous case, we were measuring the reflection, but in this case, we are going to measure the transmission. Okay. This is the other type of structure, and here we can see that due to this resonating structure of this kind of a semicircle and umbrella type door type structure, we are getting these peaks. Okay. The good thing is that these peaks are very sensitive to the background reflective index. As you can see that when the reflective index is 1, the red peaks you can observe. When the reflective index is 1.4, then uh, you can observe the shift in the resonance peak. You can observe. Okay. Now we are changing the reflective index from 1 to 3.6. Remember in the last case, the shift in the reflective index was 1.8 only. Here I'm just making it double, 3.6. So up to this point, we can actually detect, even though we can go the larger value also, because there is no distortion in the peaks occur. So we can go to the higher value of refractive index also. So actually what is happening, that when you are changing the refractive index, the red curve showing that there is no dip, the blue color is showing that there is a dip. There is a dip. Dip means the value is less than minus 20, minus 20. So, and even though you can see that yellow color from the yellow color, if the dip is below the minus 10 decibel, we can consider it as a resonance. So yellow color showing that there is a dip. So, and the red color is showing that there is not a dip or there is no resonance. So you can see here as we are increasing the refractive index, all the peaks are shifting. This peak are shifting, but the shift is very small, or you can say that the sensitivity is little bit small, but shift you can observe. The second peak, by looking at the slope, it is relative to the first peak. The second peak is more sensitivity. The slope of this peak is very high. This one is also very high, and this one is the maximum. So what actually you observe that this peak or the fifth peak, the resonance which occur at 2 terahertz, means this peak, the last one peak, the fifth peak or fifth dip, are very highly sensitive to the background effective index. The other peaks are also very sensitive, but that is not a very high sensible. These are relatively lower sensible for comparison to the last peak. But all the peaks are sensitive to the, but all the peaks are very highly sensitive to the background effective index. So what actually is showing that when you change the background effective index, you can actually detect when we are changing the background effective index, the shift in resonance frequency occur, and if your samples have others other than tuberculosis, which have like cancer cell detection. Various cancer cells have a refractive index in between these two to 2.5. In this refractive index range, you will find that the various cancerous cells. So you can use this sensor to detect the cancerous cells like breast cells or cervical cells and cancer. The other sensor you can use this device to detect those type of sensor. Even though because this device works for the very high refractive index, so you can also use this for the other industrial application to detect the harmful hazardous gases which have a refractive index in this range. Okay, so this is a very uh, highly detection grade sensor which I am showing here. So, okay. Whenever you design the sensor, this is a very important that you to check its performance for the different angle of incidence. Angle of incidence means you can see that by which angle the electromagnetic wave is incident on it. It is not necessary that your wave will come at only everywhere at the same angle. This may be the possibility that your wave will come with this angle with the normal is something theta 1. Let us suppose this theta 1 is changing. It can be of different angle of incident. So you should design the sensor such that this will work for almost all value of theta. But in this case, you can see that first two peaks are working perfectly up to theta equals to 45 degree or 50 degree. You can say that up to theta equals to 42 degree, 50 degree. First two peaks are very good. They are giving the dip, even though in the third peaks are also yellow, fourth peak are also yellow. But fifth peak is performance is degraded. So what you actually we can say that theta, when you're wearing the theta up to theta 50 degree, your device which you have designed is performance is very good. Again, when you check the polarization dependence, phi is polarization. Polarization means whether this device will work as a x polarized way and y polarized way. So no, this will because this is a polarization dependent, because as you're changing the polarization angle, the system performance is changing. So what it means that this device will work for a particular polarization when phi is 0 degree, but the polarization when the polarization of the angle is changed, this device will not work perfectly. So this is the disadvantage of this proposed device. This we are trying to work on. Okay, this is another example. Now this is the third type of sensor, and this is a graphene-based biosensor. Actually, it is a multifunctional device. Multifunctional device means that this can be used for two purposes. Okay, before going to that, let's just quickly just know the what is graphene material. Graphene is a of course very thin material whose property can be controlled, or you can say that whose conductivity can be controlled externally by changing the chemical potential. So this graphene is placed at the top of the structure, and by just giving some biasing voltage or changing the biasing voltage, actually we can change the graphene potential. We can change the graphene potential, chemical potential. So chemical potential, when you are able to change the chemical potential of this graphene material, this conductivity is changes. When the conductivity is changes, its performance is also changes. So what is the point here, that by single device after the fabrication, you can use it for the two function. You can use as a electromagnetic shielding, or like there are some reason you don't want any electromagnetic wave. You can use this as a shielding device. It will not allow any electromagnetic wave at that reason. Or you can say that it is something like a jammer which block all the electromagnetic wave which lies in that frequency range. So this device can act as a jammer or electromagnetic shielding device, which have a when the chemical potential is 0 electron volt, and this is actually the showing the reflection and transmission and the shielding effectiveness, which is very high. But I'm more concerned about the sensing part. So I'm coming to the next. So the same device act as a sensor. You change the chemical potential 0.9 electron volt. So this is a very novel things. Actually, we are able to do two function with the same device, just only changing the chemical potential. That is the novelty of this work, and that is why it is published in the TCAS transaction and circuit and system. And this just changing the chemical potential we can use as a sensor, and we can use as a shielding or a jammer. So when the chemical potential changes to 0.9 electron volt, so this device act as a sensor, and one of the peak is very highly sensitive to the background effective index. As you can see that the absorption phenomena is this absorption peak is very high. This is a zoom version of this. It is very highly sensitive to the background effective index. When it is air, it looks like this. When it is changing 1.2, 1.4, 1.6, the refractive index, the shift in the structures. Okay. Okay. So with this, we can overall what we can say that beta surface is a very important or very useful techniques or very useful device which you can incorporate in any sensing devices to reduce or improve the performance. So you can if you have a pressure sensor, if you have a like a biosensor, like till now I discussed about the biomedical application, so you can actually reduce the complexity. Another example, I'm showing that, of course, the pressure sensor. It is not related to the biomedical application, but I'm showing that how this meta surface can be used as a sensor to sensing the pressure. So this device can also be used as a pressure sensor, like it just simply showing the it is an anechoic chamber or lab based how you can perform the pressure sensor in the lab. This is an anechoic chamber. You have a two horn antenna which is connected with the vector network analyzer, which is this. Practically, you will find that vector network analyzer will look like this. You have a superstrate, which is a flexible material. You have a meta surface, which this is a side view. Actually, it is not the top view. So side view it is showing that this is the meta surface, which this is a periodic structure. This is a substrate, and this is the metallic ground. Now you're applying the pressure from the top. Before applying the pressure, actually we measure the behavior. We transmit the signal from here and receive the reflected signal from this antenna. So when you do not apply the pressure, the resonance peak is observed as a red curve. You can see here as a red curve. But once you apply the pressure, due to this applying the pressure, this air, because this is a flexible material and it is placed on a fixed support. So this thickness of this superstrate will get reduced because it is a flexible material. This thickness of this will get reduced, and this air gap start filling with this superstrate. What is actually happening indirectly? The capacitance of the structure of this behavior, effective capacitance, is started changing, and you can see that C equals to A epsilon of what D. This capacitance start increasing actually when the capacitance start increasing. So if you know that resonance frequency is F equals to 1 upon root over LC. So when F equals to 1 upon root over LC, resonance frequency. So if the capacitance increases, the resonance frequency will get reduced. And C is equals to, for the parallel plate capacitance, A epsilon naught divided by D. This is A is the effective area, epsilon naught is the permittivity between this space, and D is the area. So here actually we actually increase the area of this, filling the area with this superstrate. So this actually increase this area is reducing because thickness of the superstrate is reducing. This D is decreasing. This will effectively increase this capacitance. When the capacitance is increased, the resonance frequency will decrease. So when you apply the pressure, due to the capacitance increase, resonance frequency will shift. So you can see here that resonance frequency after the pressure, it is shifted to the lower frequency, and by just shifting of this frequency, you can actually detect that whether this is working as a pressure sensor or not. Okay. How much time I have, Yumesh?
Sir, you have another 5 to 10 minutes, sir.
Okay, okay. I'll try to finish in 5 minutes. Okay, so this is a pressure sensor, how it works. So this is the structure which I have shown. I have shown the principle here. This is the structure which is from the top. You can see that this is the superstrate polycarbonate which we have used polycarbonate as a superstrate. Middle that this is a metal copper thing, copper resonating structure, and this middle Roger 300 substrate, and the bottom is the copper layer. And when we apply the pressure, when we don't apply the pressure, the peak are as a black curve. When you apply the pressure, it is like a red curve. So in the resonance shifted when you apply the pressure, and in the absorption, this is also observed. So this is showing the behavior. Actually, the resonance. Why this resonance occur? You can see that because the resonance is occur at three different frequency: 25.54, 28.1, 28.9 gigahertz, and 33.6 gigahertz. So this resonance is occur because we have used three brick here, or in our language we use three dipoles here. This dipole, the dipole which have a larger length, will show you will resonate at 25.54 gigahertz. That's why you can see that at 25.54 gigahertz, most of the electric field is concentrated in the larger dipole. But at the 28.91 gigahertz, most of the electric field is concentrated in the middle one, and at 33.621, most of the electric field is concentrated at the lower one. So this shows that three different dipoles are responsible for the three different peaks. Okay. I'll not go into the detail. This is not a sensor. This is also another type of sensor, which is a hyperspectral image sensor, which is we are working here. This is a ISRO project where actually uh, the satellite images, which is coming at the satellite images, from the satellite images, we have to actually detect whether that images from that images we have to detect whether in that image there is a vegetation or there is a water or a soil is there or not. So that type of sensor is called the hyperspectral image sensor, and we are developing this type of sensor here at NIT Patna. To from the image, we will have to detect the different things. These are the some hyperspectral image processing things. Hyperspectral means this the continuous spectrum, and these things can be used. This hyperspectral image sensor is used at airplanes, helicopters, satellites, fixed wing UAV, and multi UAV. You can use. There are some theories how we can use how the working. This is the working of the hyperspectral image sensor, and okay, I'm not going to the detail of this. Okay, I just showing that how what mirror surface is doing. You can see that this is a conventional hyperspectral sensor. Means you have so many spectrometer, gating, shutter, beam splitter, mirrors. You can see this is a very complex things. This is a complex hyperspectral, conventional hyperspectral system. But when we introduce the metamaterial hyperspectral system, you can see that things are very easy. Means that system become very initially it was very complex, but it is very simple now. System size will get reduced, and it is very easier to fabricate, and it is very easier to incorporate it anywhere. So what actually the metamaterial do? So metamaterial, by incorporating the metamaterial in the system, you actually are reducing many things. Okay, this is some fabricated things. Here you can see that this is your DBR, this is your DBR, this is your metamaterial structure, which is and this is another material, cavity material. These are the things. What are the requirements for the hyperspectral image sensor? And this shows the material which we can use. Actually, we are working on the mid-infrared region. So this is the mid-infrared region which actually we wanted to do these materials, and this material can be used for the fabrication of hyperspectral image sensor. These are the one of the previous work done, which is not done by. This is the work done by our lab, and we designed the hyperspectral image sensor which can sense the light which have a wavelength of 4,700 nanometer that can be detected, or like suppose soil have a different wavelength, vegetation have a different wavelength. So let's suppose the vegetation have which is emitting the light have a wavelength of lambda 2 or 4,500. So it can be detected by this speed. So this is another things which we have designed in our lab, and these are showing the uh, parametric variation. Means that how you can, by varying these things, you can actually check that the response of the sensor is very similar. The metal surface can be also used as RF energy harvesting. I'm not going to the that deep. Okay, these are the work done which we have done in our lab. RF energy harvesting means that whatever the RF wave in your ambient, we can store it and we can use it as a power for the low power devices like IoT based sensor. Okay, these are the done which we have done. Okay, the last one application, that meta surface can be also used as a focusing device like a lens. So you can use a meta surface to focus the light or electromagnetic wave. This is also a very important application which we use in a biomedical or in a medical field. Like some in some surgery, you need concentrated electromagnetic wave at some point for some laser operation. In that case, you need some devices to focus on a particular very narrow area. So at that time you can use this focusing device to focus on that all the way which will wanted to focus on particular area, not on the other area. Like because if you operate your body with some electromagnetic wave, that electromagnetic wave or other wave are harmful to your organs. So you have to avoid those organs with to come in, to radiate or to illuminate with this EM wave. So you can use this focusing device so that this all the wave which is going to the your body, it will focus on the particular area where you wanted to operate, and at every other area the EM wave will not be the EM wave intensity will be zero. So by doing this, your organ will not be affected by that harmful EM wave. These are some techniques for how we can achieve the metasurface focusing. You can see that we have achieved a focus at the center. Okay, so this is just I wanted to acknowledge that this is a SAC which we are giving Mr. Ankur Jain, which is from the scientist app in the SAC, providing the funding to us. Dr. Srilal from the VSSC ISRO is providing the funding for the pressure sensor, and the Soumik Bhattacharya sir also working with me on various projects. These are my PhD scholars which are working with us on different topics. With this are sensor. Any, if you have any question, thank you so much. Yeah.
All the participants are requested to get interact. I have given permission to unmute yourself. So there were a question actually in the chat box. They asked, what does metamaterial mean?
A metamaterial, as I said in the beginning, starting slide, that metamaterial is something which you have if you have some structure and you periodically arrange it in the 2-dimensional, 3-dimensional, and then that is called a metamaterial.
Yes, Ashok Bera sir, you can ask. I hope that was your
हाँ जी
question
सर,
which I
हाँ
asked.
जी सर,
Yeah,
नमस्कार जी। सर नमस्कार जी। सर मैं पूछना चाहता हूँ कि सर ये जो आपने मेटा मटेरियल बताया, हमें ये तो बाउंसर बॉल जैसे बाउंस कर गया हमारा माइंड से, क्योंकि हम इस एरिया के नहीं हैं। आप हमें सिंपल बताइए इसका यूज क्या होता है प्रैक्टिकल लाइफ में, और हम क्या कर सकते हैं हेल्थ केयर फील्ड में। जैसे कि आई एम फ्रॉम हेल्थ केयर डिपार्टमेंट, तो हम भी सोच सकते हैं कुछ बनाने के लिए। आपका मटेरियल का एग्जांपल्स क्या था, आपने क्या क्या यूज किया था। जैसे हम नानो पार्टिकल बनाते हैं तो पॉलीमर्स यूज करते हैं, ऑर्गेनिक मटेरियल्स यूज करते हैं, इनऑर्गेनिक मटेरियल्स यूज किया जाता है। तो आप मटेरियल्स के लिए क्या क्या ऐसे चीज रखे हैं। आपने तो बहुत सारा नॉलेज दिया जैसे फिजिक्स का ऊपर, इतना नॉलेज नहीं है सर। तो हम ये जानना चाहते हैं आपका जो नॉलेज आपने दिया, इसको हेल्थ केयर में हम कैसे अप्लाई कर सकते हैं, पहला चीज। और दूसरा चीज है कि ये मैग्नेटिक प्रॉपर्टीज है, तो हेल्थ केयर के साथ इसका क्या रिलेशन होगा, हम कैसे एप्लीकेशन सोच सकते हैं। प्लीज गाइड अस।
ओके, क्वेश्चन किसका था?
Ashok Behra.
So, okay, Ashok ji, okay, since you are not in that field, I can understand. The metamaterial, something it is, you are it is a periodic structure, metallic periodic structure. Actually, the things which I have shown, that at the top there is a metallic periodic structure, and the middle layer there is a substrate of Rogers, and the bottom layer there is again metal or some other structure. Okay, and this is actually the fabrication point of view. Now you are asking that in the simple manner how you can use this metamaterial, how it is helping in the health sector. As I showed in the previous slide, that we can design the sensor by using this metamaterial, and this sensor can be used for detecting the tuberculosis, cancer cells. Those things can be this things can be detected by using those sensor.
राजन सर, मैं उनको क्लियर
सर
करूं एक
सर
वर्ड में?
जी,
सर
यस
बैरा
सर।
सर
जी,
सर
बैरा
सर
जी,
सर सर हाँ सर।
एक्चुअली मैं क्लियर करता हूं,
हम्म,
because more actually is like we are like in collaboration, so I know few things that I will share you. The thing
नो
is
इशू
that
सर।
अगर आपके पास सेंसर है, ठीक है, फॉर एग्जाम्पल एक एंटेना है,
हाँ,
आप अपने पीछे बैक में लगा देंगे या साइड में लगाएंगे और ब्रेस्ट कैंसर को डिटेक्ट करना नॉन इन्वेसिव वे में, तो उस वक्त हम लोग एक रे पास करेंगे, एक रे मतलब एक इलेक्ट्रोमैग्नेटिक रेडिएशन पास करेंगे और कैंसर है कि नहीं करके डिटेक्ट करेंगे। जैसे थर्मल इमेज होता है ना, ब्रेस्ट का थर्मल इमेज लेकर हम लोग बताते हैं कि कहाँ पे हीट मैप होता है ज्यादा। सिमिलर में
या
नॉन इन्वेसिव वे में वी विल वी विल हैव ए स्ट्रक्चर कि कहाँ पर हम लोग का ये ब्रेस्ट जो कैंसर है, कहाँ पर वो ट्यूमर है कि नहीं करके, समझ रहे हैं आपका?
नो
प्रॉब्लली
सर,
यू
आई मीन
माइंड।
या आई एम अंडरस्टैंडिंग, बट आई एम नॉट अंडरस्टैंडिंग वन थिंग कि देखिए कि हम उस केस में पेशेंट को हम लेटाया जाता है, पीसीटी सीटी स्कैन में हो, और उसके बाद कुछ खिलाया जाता है, उसके बाद
नहीं नहीं, ये नॉन
जाके स्कैन।
इन्वेसिव है, ये नॉन इन्वेसिव है, यहाँ पर कुछ भी नहीं देंगे हम लोग,
हाँ तो
कुछ
क्या
भी नहीं
कैसे
देंगे
होगा?
हम लोग।
कैसे होगा? इज इट लाइक कि हम क्या करेंगे? सेंसर इज ए हार्डवेयर, नो, सेंसर इज
ना
ए
ना ना
बेसिकली
ना,
हार्डवेयर, आई थिंक।
सेंसर एक्चुअली देखिए, अभी लीड लीड रखते हैं ना, लेड का शीट रखते हैं किसे,
हाँ हाँ,
रेडिएशन को
या
अवॉइड करने के लिए ना, बाहर ना जाए।
यस यस,
सिमिलर
बाहर
वे
ना जाए,
में
या
लेड के बदले में यहाँ पर हमारा सेंसर का प्लेटफॉर्म रहेगा, ठीक है, मतलब बॉडी रहेगा,
ओके
बॉडी के पीछे या साइड में सेंसर का प्लेटफॉर्म रहेगा। यू विल
ओके
सेंड ए इलेक्ट्रोमैग्नेटिक रेडिएशन, ठीक है।
ओके।
हाँ,
हाँ
वो क्या करेगा, अगर रिफ्लेक्ट होकर वापस जब मिलेगा हम लोग को, दैट टाइम इट विल हैव द इंफॉर्मेशन,
Okay.
राइट सर?
Yes, yes.
एनर्जी
Actually, you can
एनर्जी।
understand. You can understand with this diagram. If you see that, आप एक्सरे करवाते हो, आप एक्सरे कराते हो तो आप अपने बॉडी को एक मशीन के आगे रखते हो, ठीक है।
या
तो अपने बॉडी को एक मशीन के आगे रखते हो तो आपके बॉडी के पीछे जस्ट वो एक मेटल रखते हैं जिसपे वो पूरा आपका बॉडी का छाप चढ़ जाता है, फिर उसको प्रिंट निकाल के दे देते हैं, ठीक है। तो वो एक्सरे क्या होता है, बहुत हार्मफुल होता है आपके, दैट यू कैन नॉट डू इन द रेगुलर बेसिस। बट ये क्योंकि बहुत हाई फ्रीक्वेंसी की होती है, हमारा जो ये होता है, ये एक्सरे नहीं है, मतलब दैट इज ऑल्सो ईएम वेव, बट विच हैव अ वेरी हाई फ्रीक्वेंसी, and what I am showing the EM wave which have a very low frequency which is not harmful for the body। अब उसके बाद वो कैसे काम करता है, लाइक एक एंटीना लिया जिससे वहां एक मशीन थी, उस मशीन से इलेक्ट्रोमैग्नेटिक वेव निकला, आपका ये हमारा था सेंसर था, उस सेंसर को मैंने उसको जो भी सैंपल था उसमें उसको ब्लड सैंपल या फिर ट्यूबरकुलोसिस सैंपल को मैंने उस पर डिटेक्ट किया, लाइक क्योंकि इसमें तो प्रेशर सेंसर, इसलिए इसमें आप नहीं समझा पा रहा हूँ, लाइक ये है आपका, ये आपके इस सेंसर को आपने आपके ब्लड सेंसर में आपको डुबो दिया, ठीक है। तो ब्लड सैंपल जो था उसमें डुबो दिया और ऊपर से हम इलेक्ट्रोमैग्नेटिक वेव को उस पर डाल रहे हैं, जैसे मैंने अभी आपको मैंने सेटअप दिखाया, ऊपर से इलेक्ट्रोमैग्नेटिक वेव गया और यहाँ से वेव रिफ्लेक्ट होकर वापस आएगा तो फिर इस वाले एंटीना से रिसीव होके फिर हमको वो डिवाइस से बताएगा कितना शिफ्ट हुआ। अगर शिफ्ट नहीं होता है तो फिर हम कहते हैं कि जो हमारा ब्लड सैंपल वो नॉर्मल है, अगर वो शिफ्ट हो गया तो वो कहते हैं इसमें उस सैंपल में कुछ ना कुछ गड़बड़ी है, वी नाउ नीड टू फर्दर डायग्नोसिस। और सिर्फ आया मतलब ट्यूबरकुलोसिस हो सकता है या कुछ हो सकता है, समझ में आया आपको?
सर।
दिस
सर
इज
और
हाउ।
5 मिनट हो सकते हैं सर? सर 5 मिनट और है क्या? थोड़ा डिस्कस कर सकें यार, आपका लेट हो रहा है, बस मुझे ये जानना
नहीं
है, मैं
नहीं,
थोड़ा
लेट हो
क्वेश्चन
रहा है
पूछूंगा।
एक्चुअली, वी नीड टू मूव ऑन टू
ओके
नेक्स्ट पर्सन। आप चैट बॉक्स में मैसेज ड्रॉप करिए, आई विल गेट यू द आंसर।
नो इशू, नो इशू सर, ओके,
ओके।
थैंक यू।
एनी
बहुत
अदर
अच्छा वर्क है
क्वेश्चन?
सर। सर बहुत अच्छा वर्क है। अगर आप थोड़ा सा जैसे कि आप बताए ना सर, प्रैक्टिकली जैसे कि कुछ एग्जांपल देके अच्छे से बताते, बहुत अच्छा लगता। अभी
नहीं
तो मैं
नहीं,
समझ
वही तो
सका
बोल रहे
कि
ना,
या
एक्सरे
इससे
वाला चीज जो
इससे
सर बताए थे
या
वो अच्छा एग्जांपल है।
मगर ओके सर, मगर यहाँ पे आप जो इलेक्ट्रोमैग्नेटिक रेडिएशन का कौन सा रेंज ले रहे हैं? कॉस्मिक रे, गामा रे, एक्स रे, यूवी,
ना
विजिबल,
बहुत
आयन,
कम है,
मैग्नेटिक रेडियो,
माइक्रोवेव,
कौन सा ले रहे हैं?
माइक्रोवेव।
माइक्रोवेव।
माइक्रो, ओके, माइक्रोवेव रीजन लेते हैं, ओके
हम्म।
फाइन, ओके। तो आपने जो प्रैक्टिकल किया, कुछ आपको रिजल्ट मिला है सर? आपने तो काम कर रहे हैं ना, दैट आई एम आस्किंग। आई हैव यू
आपको
गॉट
मैंने
एनी
आई
डाउट?
हैव मैंने दिखाया, आप कुछ कुछ प्रैक्टिकल वेव दिखाया था मैंने, यहाँ से भी हम लोग का खुद का लैब का फैब्रिकेशन है, ये है, ये है, यू कैन सी दैट, here the samples place होता है, फिर यहाँ पे 2 एंटीना लगा के हम लोग उसको सैंपल मेजर करते हैं. This one is also one of the measurement. So we have done some part, but that sensing part was that was the simulated one.
Yeah. Okay, fine, sir. Nice work. Thank you.
Okay, sir.
Thank you
Thanks
very
for
much,
your
sir.
time.
Thank you very much, sir, for engaging in thoughtful, provoking session. Your insights into the metamaterial-based biosensors for biomedical applications, especially the discussion on design strategies and sensing mechanism, added great depth to today's program. As we approach concluding phase of this week, your lecture provided valuable perspectives that enriched our ongoing discussions. Now, as a token of, now I would request Dr. Yumnesh Kashishwanathan to present token to our respect and respect and appreciation. Now we would like to
Thank you.
present to
Rajan sir,
memento.
thanks for your time. So accept our token of gratitude.
Thank you so much, Yunus. Thank you so much, Dhiraji.
It was like wonderful section. So it was wonderful section where I wanted to know a few things which I got to know today.
Okay,
Thanks.
okay. Thank you so much. Shall I leave? I can leave now.
Yes, sir. Yes, sir.
Okay. Thank you.
Okay,
Thank you,
thanks a lot.
everyone. Okay.
Dheeraj sir,
Yes.
our next speaker Uday sir is online, so we can invite him.
Okay. I'm just going to start.
Okay, sir.
Moving moving forward, I am pleased to invite our distinguished speaker, Dr. Uday Shankar from FDP Varanasi. Dr. Uday Shankar is an assistant professor in the
Dheeraj sir, unmute yourself. Dheeraj sir, unmute yourself.
Oh, really sorry. Sorry. Moving forward, I am pleased to invite our distinguished speaker, Dr. Uday Shankar from IIT BHU Varanasi. Dr. Shankar is an assistant professor in the School of Material Science and Technology at Indian Institute of Technology, Banaras, Varanasi. He holds a PhD in Polymer Science and Process Engineering from IIT Roorkee, and MTech in Rubber Technology from IIT Kharagpur, and a BTech in Polymer Science and Rubber Technology from Cochin University of Science and Technology. Dr. Uday research interests encompasses self-healing polymers, vitrimers, polymer composites, and bio-based oil-spill solvents. He has made significant contribution to advanced functional materials and soft electronics with over 19 peer-reviewed journal publications, 6 book chapters, and a growing citation at index of 14. He has served in academic and industry roles in India and abroad, including a postdoctoral position at Jeonbuk National University, South Korea. Dr. Shankar has received several honors, including the Department Best Thesis Award at IIT Roorkee and international travel grants from CSIR and IIT Roorkee. In addition to his academic achievements, he is an invited speaker at national and international conference and a member of professional bodies such as CRSI, EPA, and American Chemical Society. We are delighted to have him guide us through his topic, that is polymers for biomedical applications. Sir, Uday sir, the floor is yours. Thank you.
Uday sir, the stage is yours.
Just let me share the screen. Is it visual?
Yes, sir. Do full screen. Yes, sir. Sir, it
Yes.
is visible.
Okay.
Please go ahead. The stage is yours.
Yes. Good morning to all of you. First of all, I would like to thank you, Dr. Dheeraj Ahuja sir, for kind introduction. Now I would like to start my presentation on polymer for biomedical application. So before I start, I would like to tell you about the different biomedical application of polymeric material and their composite material. So like we are using polymer and their composite for dental resin, wound dressing, bone, blood vessel, skin, and oral tissues. And here I have given some example like polyethylene, polypropylene, acrylic, and their application, like for waste baggage and their application in that different area. So basically this polymeric material can be used for medical packaging to the medical product. So this is also basically used for the implantation in the body, like hip joint, artificial heart valve, and so many other applications. So first of all, I would like to tell you about the basics of polymer. So we are having so many classification based on that, like origin, thermal responses, and mode of polymerization, and so on. So why we are discussing this? Because we know the type of polymer, they are playing the crucial role. What kind of polymer we are basically using, whether that is biocompatible or not. So that is going to be matter for biomedical application. So that's what we should understand, what kind of polymer basically we should select. So if we will talk about the origin of polymer, so we can divide it in three parts: natural polymer, synthetic polymer, and semi-synthetic polymer. So if we will extract it from the natural things like plant and that different cells, so then we can say it's natural polymer. If you little bit modify that natural polymer, then we can call it semi-synthetic polymer. And if we will prepare it by some chemical reaction, then we can call it synthetic polymer. And if we'll talk about the thermal response, so some polymer can be processed again and again. That can call as thermoplastic, and if it cannot be processed again and again, then that called the thermoset. Why that is happening? Because we know the thermoset is connected with the cross linking agent, and that bond energy is higher than that back bond with which it's formed. So if we are providing higher energy, then what will happen? Their backbone is going to be dissociate and our polymer is going to be degrade. So that's what this is showing, that nature. Now coming to the mode of polymerization. So we are having two mode: addition polymerization and condensation polymerization. I'm not going in detail for their how we are synthesizing, what is the mechanism. I'm not going to in that detail. I'm just briefly trying to tell you about the different polymer based on their way we can synthesize and their role in the biomedical application. So we can also synthesize that polymer in the way of linear, branch, and cross link, and I will correlate it with their application with biomedical part. And if we'll talk about the application part, then broadly we can divide it in three parts: fiber, plastic, and rubber. And here is their property that is listed in the table. And now if that pendant group, they are attached in some specific manner, based on that we can divide it in isotactic, syntactic, and atactic. And if we'll talk about in terms of crystallinity, then it can be divided in amorphous polymer, semi-crystalline, and crystalline polymer. So now coming to that biomedical polymers. So this is basically based on their application. We have classified and we have kept in this part, this category, biomedical polymer. So basically, what what is the requirement for any polymer which can be used for the biomedical application? So our main criteria to be used in the biomedical application, that should be non immunogenic, that should be non-toxic, that should have some certain mechanical property, certain chemical property, and certain electrical property. And especially it should have very good production rate. But ultimately when we are using, suppose we are having some problem and some disease and we are consuming some drug, so what is our consideration? That We are always worried about that, whether that drug is gonna remain in the body or after that treatment, or if we are fine with that disease, then that is going to be come out from our body, or whether it's going to be metabolized under that psychological condition or not. So that is the key point for that material before using it in biomedical application. So now, as I mentioned, it should have certain property in terms of mechanical property. So we always trying to trade off between their application part or their nature. So if we are applying some polymeric material in biomedical applications, then we should always consider in terms of their cost, their mechanical property, their density. So here is the diagram where we can see with respect to that density what is the strength. So out of the all material, here you can see polymer is having low density as well as high strength. So this is the suitable material for any other application. So now coming to their synthesis part, because this is the main part which will help us to design the polymer material for the biomedical application. So we are broadly we can divide it in two parts: addition polymerization and condensation polymerization. In addition polymerization, we can synthesize through free radical, ionic, and catalytic, and in condensation polymerization, we can synthesize in condensation polymerization, ring opening, and polyaddition. So now, what is polymerization? Polymerization means poly means many, mer means unit. We are adding so many monomer in that polymeric material. So if the starting material what we are using, that is monomer, and that if we are started preparing that polymer, so if we are giving very less time or early stage, then it is not having that much molecular weight. It is having very less molecular weight. Then we can call it oligomer. And if we are giving the proper condition and time, then our polymerization is complete, and then what we are getting, that is nothing but polymer. So now coming to the next slide, that is polymerization method and technique. So polymerization method is nothing but this is the path through which we are preparing the polymer. But technique is in that pathway, what reaction condition we are using, what medium we are using. Based on that, we can classify it in which category it's coming. So basically, we having four techniques: bulk polymerization, solvent polymerization, and bulk solution, suspension polymerization, and emulsion polymerization. So this, this picture you can see how that chain is connecting with each other. There is a certain way. Based on that, we can say whether this is the random polymer, whether this is the graft alternate polymer. So it is going to play the crucial role. Now coming to the first technique what we have already name it. So that is bulk polymerization. So in bulk polymerization, what we are doing, basically we are taking the monomer and we are adding the initiator, nothing else, and we are providing the temperature. So what will happen with that temperature? That initiator will break and it will start the initiation of that polymerization. Then it will start propagation, and at the end the termination will happen. So basically here what we are using only monomer, that is the responsible for that polymer formation, and that very less amount of initiator, very 0.01% of monomer. So you can understand how much additional material, what means how much apart from that monomer, how much percentage we have used. That is nothing. That is very less. So whatever the polymer we are getting, that is completely pure, nothing impurity. We cannot have a single or a small amount of impurity. So if we will talk about the medical application, so what kind of polymer basically we need? We need the material which is having that purity, that should not contain even that a small amount of impurity is not acceptable. So that's what this technique is very important. But here we are having certain limitations, some problem. If we will talk about the polymerization reaction, so we are giving the temperature, and then that initiator is playing the role, and that's how. And after that, their initiation, it will start propagation, and that's how it's forming that polymer. So basically, what is happening with time in that during that propagation, we are having so many free radicals. So we are having so many free radicals that is with time that is generating and they are accumulating, but the chance of termination is very less. So if the chance of termination is less, it means we are having more number of generated free radicals. Then what will happen? We will be having that heat pocket that will be generated with time, and that will lead to some maybe explosion. So that is not safe in terms of production point of view. So basically, we have to think about the their cost, their production rate, their purity, as well as how easily we can synthesize. So that's what we are having next technique, where we are adding that solution. So what is the what is the advantage we are getting over the previous one? Now we have added the solvent. So what will happen? It will reduce the viscosity with time. As I mentioned in the last technique, that bulk polymerization, what is happening? We are having too many accumulated free radicals. Now if we will add the solution, then what will happen? They are having that number of radical, but they are separated. They won't let them accumulate in their space. So what will happen? We can prevent that explosion while that producing that polymer. But now if you think in terms of medical application, then there is the criteria. We should have the pure material that is that can be used for our for the target application. Now what we have done here, we have added solvent. So with this solvent, what advantage we are getting? We can, you know, do the process in better way without any explosion. Now we are having this solvent, so the trace of solvent after the preparing that polymer, still that is gonna remain in that polymer. So it's very difficult to remove that solvent 100%. So we are having now next technique. What we are doing now, we are going to combine that bulk polymerization as well as solution polymerization here. So what is happening? We are having monomer as we have used in that bulk polymerization as well as solution polymerization. We are having initiator. That initiator is dissolved in the monomer, and then we are using water as a solvent. So water is having it's a very good solvent because it's not having any toxic nature, as well as it's very easily available. And if we'll do the reaction, if our temperature is increasing with that accumulation of that free radical, then what will happen? It will, if it will increase by more than 100 degrees centigrade, then what will happen? That water will evaporate and it will maintain our temperature. And then what we are using, stabilizer, that will stabilize that suspended particle. So what is happening here? You can see this suspended particle here. This is having monomer and it is having initiator. So like bulk polymerization, it will polymerize, and to stabilize it we are using stabilizer, that is nothing but PBA and CMC. And then after completely polymerization, what we will do, we will filter out this synthesized polymer, and we will wash it again and again to remove that impurity. But still we have added solvent. Hardly matter, that it doesn't matter whether it's toxic and non-toxic, but still it's having that water and stabilizer. So it won't give you that purity like the bulk polymerization, but it is having the purity better in terms of that what we are getting in the solution polymerization. Now moving to the next technique, that is emulsion polymerization. Here what we are using, so see what is the aim of different techniques. Our aim is to get the pure polymer, as well as to do it in better way in terms of processing. So in this technique, what we are having monomer, we are having solvent, we are having initiator, we are having emulsifier, we are having stabilizer, we are having surface tension regulator, we are having buffer solution, and we are having chain regulator. So basically, in this technique, we are having chain regulator that will, actually dictate that, chain length, whether it is having that appropriate length or not. Because we are targeting some specific application. For that application, we should have some specific property, and that property is coming from, that property is correlated with that molecular weight. So that's what this is the very, very good technique. But still, it is having less purity compared to bulk polymerization. But in other terms, it is having control molecular weight. It is having better property compared to bulk polymerization, and it's having better processing. So now coming to the, that next technique, that is interfacial polymerization. That is nothing but we are having two different phases, and they are contact with each other, and when we are disturbing, if we are removing that product, then it is going in further direction in terms of polymerization. So now we are coming to the, term copolymerization. So it we have discussed about the polymer. Now we are going to talk about the polymerization, copolymerization, or copolymer. So basically this is nothing but this is the mixing of, the property of two different polymer. So basically we are copolymerization. So we are putting, instead of one monomer, we are putting two monomer, and then we can synthesize it again through the addition or through the condensation. Sorry, through the addition with different method, like free radical polymerization, through ionic, and through cationic. So what is the need of copolymerization? So as we are well aware of that, for any chemist to prepare the material which is having different property, that is very, very difficult. In the same material, we could, to getting the 10 different property, it's very difficult. So what we can do, we can, we can try to put two or three different monomer which is having their individual property, and when we are, combining them, then they are having the property of each individual, and even in better in terms of property. So now if we are copolymerizing, then based on their reactivity ratio, R1 and R2. So based on their reactivity ratio, they can be random, they can be alternating, they can be block, and they can be graph. Now again, it is having very crucial role to use it in biomedical application. So if it is in random way, then their property is going to be something different than that the copolymer when we are forming in terms of alternating way, because it is having, see, we are combining them in a specific manner. So maybe our material can be crystalline, or maybe it can be amorphous. Then again it is having their melting point and their glass transition temperature. So that is going to play the role in terms of biomedical application. So now coming to the, some characterization technique. Out of that, basically I'm going to cover the FTIR and NMR. So suppose we are prepared some material and we are claiming that it is going to be used, we are going to use that material for the biomedical application. So first point is coming, whether is it pure. Second question is coming, whatever the material we are claiming, whether that material has been synthesized or not. Or third part, is there in any, chemical that is, portion that is unreacted or not. So these 3 points we have to consider. If it's completely pure, then it's fine, we can go for that biomedical application. Suppose if it's not pure, then again we have to, again we have to do some process and wash it and do it in some specific treatment, so we can make it in better in terms of purity. And secondly, suppose we have used two different monomers, one monomer is not completely reacted, so still there is a chance it can show some kind of reaction inside our body, so that is not good for our health. So that's what we have to confirm, whether our reaction is completed or not. So here we can see we have copolymerized methyl methacrylate and acrylonitrile. So here we can see we have given some condition like 80 degrees centigrade temperature and 6 hours. Now we can see what is happening with initially when we are homopolymerizing, means when we are making that homopolymer, means PMMA, we don't have any acrylonitrile content. So here there is no any peak it is reflecting. It means this is completely homopolymer, right? And when we are adding second monomer, then we can see there is the one small peak that is generating when we are increasing the amount of acrylonitrile. So this method is confirming if we are adding second monomer, so that can be validated with this reaction. This can be also validated how much time we should give, how much time is going to be optimum for our polymerization. Now, third part is NMR, 1H NMR. That will give us the idea if suppose we are claiming this portion is 90% and this portion is 10%. So what is the the proof? How we can claim that this is in the ratio of 90 is to 10? So with that, we have performed that 1H NMR and we have confirmed that they are in the ratio of 9 is to 10, they are in the ratio of 80 is to 20, they are in the ratio of 70 is to 30. So now the question is why we are making in different ratio. First, we will prepare different ratio. In that ratio we are preparing that polymer, then we will go for their property, their mechanical property, their electrical property, their chemical, different property we will get it, and then we can compare which material is going to be suitable for our application. So this is the our motive to show you this characterization technique and to tell you about the synthesis process. Now coming to the I was talking about the property. So see, I was already mentioning you about the preparation method of that polymer, then processing and their application. So I have already told you about the different technique where we are getting the pure one or where we are getting the better property. Now second thing, also suppose we are making some medical device. So what we need, we have to process that material, we have to pass through some machines, but now the matter is whether it is having the low viscosity or not. Why we are talking in terms of viscosity? If it's having very high viscosity, then it's having difficulty to process that material and to make that instrument out of that material. So that's what we have to trade off between that molecular weight as well as their property. So if we are optimizing certain method, then we have to think about their molecular weight. So accordingly we have to optimize the time, we have to optimize the temperature. Once we done it, then we are having that idea about the viscosity. Now here you can see in this plot, once you are having higher molecular weight, means with increase of molecular weight you are having increase in the viscosity. So after certain time there is a saturation, although your molecular weight have been increased but your viscosity is not increased that much in that ratio. But what is the impact on that property? Here you can see with the increase of viscosity or with the increase of molecular weight, what is happening, you are having increase in tensile strength, but after certain time, after that critical molecular weight, you are having saturated property. So it means we don't need high molecular weight, we need that critical molecular weight so that we can get the best mechanical property or best required property, as well as we can process it in better way. Now you can correlate here by different mechanism through which we are polymerizing that material. So if we are using that free radical polymerization, so starting itself we are getting that high molecular weight of that that optimum molecular weight of that material. In the case of ionic mechanism, it is having that increase of molecular weight with time. That is, and here you can see in the step growth polymerization, it's very difficult to get the high molecular weight until unless you are going for that high conversion, like 99%, even more than that. So this is how it is related with that, that the concept of polymerization. So how we are polymerizing, what is the molecular weight we are getting, and what is their viscosity. Based on that, we can optimize the things, and we can claim that okay, this is the material we can choose and we can use it for biomedical application. So there are so many specific application. Out of that, here I have selected the different polymer. Here you can see methacrylates, that polycarbonate, that PEEK, that chitosan, and so many other polymer, PLA, different polymers. Only these polymers, see, this is the only few polymer which I have listed here that can be used for dental application. So now again, we have to be very specific whether we are using it for dental application, whether we are using it for hip replacement, whether we are using it for that transplant, whether we are using it for wound healing. So for what application we are targeting, based on that we have to select the material. Now coming to the our few research work, means my research scholar they are doing. They have just started, as Vijay sir mentioned about my academic journey. Very recently, last year I have joined the IIT BHU, and I have set up my lab, and my research scholar they have started working in this area. So they have just started preparing the green through green synthesis. They are preparing the nanomaterial. So what is happening? Basically, they are preparing the nanoparticle, like silver nanoparticle. They are preparing through that green method. So basically, they are taking the plant extract, and it is having something which is reducing that that metal and making it that nanoparticle, right? So and then we are entrapping that nanoparticle in chitosan, that is biocompatible material, or that is or that can be help for that for controlled drug release or for some targeted application. Now I would like to tell you about the one of my piece that research work which is published in ACS Applied Biomaterial. I worked as a co-author, and this is in the collaboration with Mukhopadhyay sir, IT Indore. So basically, what we tried there, we took the that silken mesoporous particle that is used as a carrier, and we have taken that zinc nanoparticle, and then finally we entrapped it in chitosan.
Hello, Dr. Uday. Dr. Uday.
Dheeraj sir,
Yes.
please make a call to Dr. Uday.
Okay.
Okay.
सर आपका डिस्कनेक्ट हो गया था नहीं कुछ नहीं
Hello, am I audible? Hello.
Yes, you are audible, Uday sir, but your screen is not visible.
Okay, okay. Just let me share the. Is it visible now?
Yes, yes, it is visible.
So, so where I have missed in which slide?
You left on 33rd slide, sir.
33rd.
Yes, yes, sir.
Okay, okay, okay. So here I was discussing about the one of our piecework which were done in collaboration with that Mukhopadhyay at IIT Indore. So basically here we tried to use that zinc nanoparticle. So that is used to target that cancer spot, and for that we use that silica mesoporous particle as a carrier, and we have entrapped it in chitosan, and then we use it for that cancer treatment. And now I have this is my research group. So from left, Iska Gupta, she is research scholar. This is Sudhir Kumar. He has completed their master thesis under me, and he is currently doing the master thesis under me. And this is Sangeeta Kitcher, research scholar. And I would like to thank my collaborator, Professor Anashya Bandyopadhyay from IIT Roorkee, Professor Pralay Mathi, IIT Varanasi, Professor Vivek Verma, IIT Kanpur, Dr. Sushant Sethi from IIT Dharwad, Professor Gaurav Manik and Pardeep K. Maji from IIT Roorkee, Dr. Vanu Pratap and Ashok Kumar from CSIR NPL New Delhi. And I would like to thank funding agency IIT BHU or MNIT for their seed grant, and Korean Institute of Marine Science and Technology for their postdoc fellowship, and CSIR and DORA IIT Roorkee for their travel grant, MHRD for MTech and PhD fellowship. Thank you.
So now we have time for question and answer. I have given permission to all the participants. They are now allowed to unmute themselves. So Ashok Veraji, you can go ahead with your question.
हाँ जी सर। हाँ जी सर, डॉक्टर उदय सर,
Yes.
नमस्कार सर।
Namaskar.
सर नाइस प्रेजेंटेशन। सर मेरा एक
Thank you.
क्वेश्चन था, आपने जो लास्ट स्लाइड दिखाया जिंक एनडीसी, व्हाट इज दैट एनडीसी एंड ये कैसे और किस तरह से टारगेट कैंसर के पास टारगेटिंग हो रहा है, व्हाट इज द मैकेनिज्म बेसिकली, ये थोड़ा
So,
एक्सप्लेन करेंगे। और
see.
दूसरा क्वेश्चन
हाँ.
सर, दूसरा क्वेश्चन है कि आपने जो इतने सारे पॉलीमर दिखाए,
हम्म.
टाइप्स ऑफ पॉलीमर व्हिच इज ब्रांच लीनियर, तो वही ब्रांच है लीनियर है तो उनका एप्लीकेशंस क्या है, और जो पॉलीमर्स है ऐसे
हम्म.
कुछ आप जो मार्केटेड फॉर्मुलेशन बताइए जो कि ब्रांच का भी हो या लीनियर का भी हो, मार्केट में अवेलेबल है प्लीज।
See, so have you seen that that day-to-day life we are using that polyethylene, right?
या
Polyethylene, polybag we are using, right? So one polyethylene is that one. Another polyethylene you have seen, that is the pipe that is made up of the polyethylene. Have you seen it?
that
Huh.
that I understand, but what
Huh.
about the in the healthcare field as a medicine,
Huh.
as
No,
a
no,
medicines we are
no, no,
using,
no, no.
yeah, healthcare.
I was talking just I was giving you the answer of that one of your questions about the linear as well as that that branch
Branch,
as well as
branch,
crossing.
yeah.
So I was
Yes
giving
sir,
you the
please.
example of that. So is it okay now? Can you able to
Yes sir.
understand that?
Sir,
So
which one is for the
uh,
pipes, the PVC pipe, they are the
huh,
linear or branched ones?
no. So in see. So in the case of PVC and polyethylene, based on their structure, we can say whether this is linear one, whether it's branch one, right? So it is having the pendant group that is going to be decided. So in the PVC, that is PVC, that is nothing we can do. In the case of polyethylene, based on their synthesis, how that is whether see that polyethylene we are using, that is having different grade, whether that is low density polyethylene, high density polyethylene, or whether it's ultra high density polyethylene. So what is happening, that polyethylene, they are having a small, that pendant group, that is nothing but hydrogen. So what is happening, it is having, very good tendency to, align with each other, over each other. So in that case, we are having high crystalline, but that is not in the case of PVC. So that's what I have given you example of polyethylene, that polybag what we are using, and that pipe that can be made of that polyethylene, right? That cannot be the case of polyvinyl chloride, right?
Okay.
Hello. Or in another term, you can understand. Suppose for that, you have seen that refrigerator, that freeze you are using in your house, that is polystyrene, right? So
Yeah.
in the same polystyrene, you can see that is very, very transparent in nature, right?
Which
Isn't
part,
it?
sir? Which
All
part of the fridge is that is transparent?
that you can
Polystyrene.
see that vegetable and something you are keeping inside that freeze, and that
Yeah, yeah, yeah.
box
Understood.
that
Tray,
is
tray.
Tray.
transparent,
You are
right?
saying
Tray,
you are saying the
right?
tray. Yeah.
Tray.
Yeah.
But same tray, if we can make with that polystyrene, and if we will co-polymerize with other material which is non-transparent in nature, then they are not going to retain their property. Now, why that is happening? Because their nature from amorphous to, uh, it's changing from amorphous to crystalline nature. That's what I am trying to explain you. That nature of that linear, as well as the different addition of different monomers, they are changing their property, right? So now, if you have to make that some device or some medical application that should be transparent, so now you have to design what material you should choose and in what
Yeah,
ratio you should,
polystyrene.
right? Okay. So is it okay
Polystyrene.
now?
Yeah,
Okay.
yeah.
Now coming to the
Sir,
second question. Yes. Yes.
sir, sir, that question you said that is polystyrene is clear, I understand. But
Huh.
that is the branched one or linear one, sir? It doesn't matter. It does not matter if a polymer is branched, and it does not matter if polymer is a linear. How the
No,
property change exactly?
no, it's a matter. That's what I'm trying to explain. Try to visualize it. What I'm trying to explain you, see, what is happening. If it's suppose, if we are having this two layers, it's very easy to, overlap or come over each other. Suppose if it is having that side chain on this, you know, on this hand. Now, can you able to bring this hand over this hand? Is it possible? Completely, can we
No,
bring it? No. So what is
no.
happening? It's having some gap. So in that case, suppose if it is linear and it don't have that much, side group or
Branched.
pendant group. So if don't have, then it's having tendency to completely overlap over each other. So in that term, it can make the material crystalline. In that case, you will be having, that opaque nature of that material, right? Suppose you are having amorphous material, it is having some kind of pendant group on something, so another chain is not going to come over each other. They are having some space. They are having amorphous
Mhm.
nature. Now it will show you the property of some kind of transparency.
Yeah,
Is it okay?
yeah, yeah, yeah. Clear.
Yes.
Yeah.
What else?
Yes, sir. Yes, sir. My question is that how the cancer is targeting the zinc
Yes, yes.
elimination.
Okay. Just coming to that slide. So,
And
as I
sir,
mentioned,
sorry,
yes.
sorry.
Huh.
Here that slide you show now, that characterization part, how you synthesize that polymer. One of the slide you show that
Huh.
synthesizing the polymers, right? No.
Okay.
So yeah, yeah. This one. NMR or IR slide where you show. Can
Okay.
you go? Yeah.
Yes.
So can you tell me when you synthesize? Yeah, this one. You synthesize this material using AIBN. Now you did the IR and you did the NMR. So have you not purified or it is purified one? How you did the purification? Because reactions are not completely 100%. No. So can you please in brief that purification part? I can be thankful to you, sir. Non audible, sir. You are not audible, sir. Mic is switch off for us. Sir, voice is not coming.
Am Hello.
Yes, sir. Go ahead. Go ahead. Yes, sir.
Yes.
Go ahead. Go ahead.
Okay. So what I am trying to explain you, when we are doing synthesis, so we are having, hello.
Yes,
Yes,
sir.
sir. Please
I'm
go
audible.
ahead.
Yeah.
So we are having some idea. Okay, we are using this chemical and this chemical. Okay, we are performing some kind of reaction, right?
Yeah.
After reaction, we are having some product, right? Still,
Yeah.
there is the possibility some of the some part of that
Reactant.
monomer is not
Yeah.
taken part in that reaction, right? So
Yeah.
what we are
Yeah.
doing now, we are having that left out that that monomer which is not taken part in that reaction, and another portion which is we are having that product which is completely got by that reaction, right? Now what we are doing, we are filtering out that material, right? And again what we are doing, we are dissolving that material in that specific solvent, right?
Sir, no,
Hmm.
sir. No, sir. See, you have taken a round bottom flask and you
Hmm.
have put the chemicals A and B and reaction completed after 8 hours. The
Hmm.
product C has been formed. The
Hmm.
product is not 100% with that A and B are also there, right? So how you separating that one?
So that's what I'm telling. Try to understand what I'm trying to say. See,
Yeah.
in the your round RB, you are having monomer, and you have performed the
Polymer.
reaction. Suppose you have
Okay.
performed the 1 hour reaction. Then what will happen? There will be some viscosity change, right? Based on that, you can
Okay.
claim that there is some reaction. Now,
Oh,
so to
viscosity. Your point is
yes,
viscosity. Yeah.
viscosity,
Yeah.
viscosity. Initially,
Okay.
see, initially you are having that low viscosity. When suppose you are having viscosity like water, and then you are having viscosity like mustard oil. So you can distinguish
Mm.
that viscosity, right? So
Mm.
similarly, in that reaction, you can see and you can distinguish between that viscosity. So what will happen after that reaction? What you can do? You can precipitate that polymer. So in my case, what we used to do, we added the DI water. So what was happening? That polymerized part, they are getting precipitated, and
Yeah, yeah,
remaining part
settle down. Yeah.
settle down, and remaining part is
Yeah.
still in that solvent form, and that is mixed with the water. So now we can filter out that part, and we can, what we can do again, we can wash again and again, again and
Yeah,
again,
yeah.
at
I
least
understand.
4 to 5 times. That's how we can
Yeah.
purify our material.
Okay.
Is it okay?
Okay. Yeah, yeah, sir. Basically, when we used to do, sir, so we used to do the column chromatography and that kind of
Yes, yes.
thing.
So
So,
it
but
depends. It
yeah,
depends. It
yeah,
depends what
but
kind of.
here, if yeah, in your case, the chromophore are not there. It's not the
Hmm.
cyclic compound. Benzene is not there, so UV can be seen. So I that's what I asked. Sir, can you please explain regarding the targeting part?
Okay, okay.
Yes.
So
I hope this will be the last question because we are running out of the
Yes, sir.
time.
Yes, sir. Last question.
okay.
Last question. Thank you,
So
sir.
so so see, this work we have published in the collaboration, and I am not the expert of that whole thing, and that hardcore chemistry. So basically, I supported in terms of that characterization part, and there few input for that that filler and all, right? So main thing, the core that core idea I would like to explain you. We are having that zinc complex. That is the reason, that is the that is the material which is going to cure our disease, right? So how we are going to take that zinc complex to that target point? So for that we need the carrier. So for that we are
हाँ
having
कल तो
silk.
सही हुआ है
Hello.
Yes, sir. Please go ahead.
Okay. So just 1 second. So that mesoporous silica, that is going to be act as a carrier for that zinc complex, and then we are entrapping this silica particle in that
Yunesh
uh,
sir,
cytosine. Hello. Yes.
Yunesh sir,
Yes. Yes.
I think we can discuss. You can discuss. You can drop your question in the chat box, and you can explain in detail there
Okay.
as we are
Okay.
running
Okay.
out
Okay.
of time.
It's fine from my
Please,
side.
sir. Please, sir. Please, sir, please. Thank you, sir.
Thank you, Dr. Uday, for your insightful and highly informative lecture.
Thank you,
I
sir.
appreciate your expertise in polymers for biomedical application. Truly enriched, this lecture truly enriched our understandings. You explained it
Thank you.
very well about the basics, fundamentals, then to advanced. So we are really thankful to you.
Thank you, sir.
Now I request Dr. Yugnesh to represent a token of gratitude to Dr. Uday Shankar.
Dr. Uday sir, thanks for
Bring
your
your lecture
time
point out.
and support. Please accept our token of gratitude.
Thanks a lot, sir. Thanks a lot for invitation, and congratulations to both of you for organizing such a lovely talk and that FDP program. So thank you once again.
Okay, sir.
Thank you,
See
sir.
you,
Thank
sir.
you.
See you.
Thank you once again for your insightful knowledge.
Thank you. Thank you. So I am leaving, right?
Okay.
Sir. You are getting late for your meeting.
Yes, thank you.
Okay, sir.
Next, it is our Dr. Yumnesh. Has Dr. Sudeep Wallace joined?
Yes, yes, yes.
Yes. Okay. Next, it is our pleasure to welcome Dr. Sudeep Paul from NIT Raipur. He is an assistant professor of biomedical engineering at NIT Raipur,
Sir,
India.
sir, associate.
Associate. I called associate only. He's an associate professor, I told. His postdoctoral research was at the University of Western Australia School of Computer Science and Software Engineering. He earned a PhD in electrophysiology and brain signal analysis from IIT BHU Varanasi. He held many workshops and conferences and published approximately 60 international national journal papers and over 50 conference papers on various platforms. He has 7 patents and 6 copyrights. He finished 20 books. Dr. Sudeep is a senior IEEE member and member of IAN, IEEE, EMBS, APSN, ISN, IBRO, and others. He has awarded the World Federation of Neurology Traveling Fellowship, Young Investigator Award, IBRO Travel Grant, and ISN Travel Award. We are privileged to have him with us to speak on the topic role of EEG and EMG for Parkinson's disease detection system. Sir, we warmly welcome you and request you to kindly begin your session. The stage is yours.
Thank you, Dr. Dheeraj. Thank you. So I am sharing my screen. My screen is visible.
Yes, sir. Yes, sir. Please go ahead.
Screen So first of all, I am thankful to Dr. Gaurav from Golgotia University and also Dr. Ubnesh from MNIT Allahabad. So they have requested me to share my knowledge in the field of the biomedical engineering, special focus to the neuroscience. I completed my journey from IIT BHU and then moved to that Perth, and I did a lot of hard work for computational neuroscience as well as the different aspects of the Parkinson disease detection system. So today I want to share you a little glimpse of just a single part of the Parkinson disease detection system. And for that, EEG and EMG has a crucial part for the Parkinson disease detection system. So if we can consider the Parkinson disease at first, so many of you heard the term of Parkinson disease. It is basically a neurological disorder, and it is coming from the brain, and due to the less of dopamine. All of you know that there are two types of the main important things are there in our brain. One is biogenic amine, another one is the that is called dopamine. One of them is the dopamine and serotonin. And except that, that is GABA and glutamate, that is also a crucial role, plays a very crucial role. But today we will focus only the dopamine. Dopamine is an biogenic amine. For that, less of dopamine, the Parkinson disease is used to be a crucial, because when the substantia nigra region of our brain having the less amount of dopamine, then the subject may suffer the Parkinson disease. And it is a non-treatable disorder. You cannot treat as a fully recovery. And there is a lot of medicines are there. But before applying the medicine, a clinician or the neurologist has to be a confirmed position that whether he or she is undergoing the Parkinson problem and how much is the Parkinson level and how it can be recovered soon. So that is the most important concept, and that's why I choose the topic that the role of EEG and EMG. EEG is basically focused on the brain, that is electroencephalogram. And EMG is basically focused to the muscle, that is electromyogram. Both are related with the Parkinson disease, because the Parkinson disease is occurring from the brain due to the less amount of dopamine in the substantia nigra, but the effect that is coming, that relate with the muscle. Because of the muscle rigidity, because of the muscle tremor, and bradykinesia, posterior imbalance, and various types of the muscle-related problem. So that means these two things, the brain and muscle, that has to be interlinked for the Parkinson disease detection system. When you go to the clinic, and if any suffering patient of Parkinson, if he or she is coming to the hospital, doctor used to ask some basic question first. If there any background of the Parkinson disease, if there any demographic, that means the demographic assay the doctor has to do. Then they have to do the different type of activity. Suppose they ask the patient to stand up, then it is very difficult to stand up. Then they ask the patient to walk it is also very difficult. Then they ask the patient for the movement, then followed by the different type of activity like grip, how much they are able to grip it properly. So different types of problems may come from the Parkinson problem. Sometimes the Parkinson patient if they are having a huge number of the amount of dopamine level, then the sleep disorder may occur. And it is one of the most important part of Parkinson problem. Because of this, sleep disorder may affect the sensory neuronal function. And for that reason, different problem may come as a psychiatric disorder, or that also relate with the Parkinson problem. So now, if we can focus to the activity, all of you know that the normal neuron of the brain that always pass through, like as suppose I am delivering my lecture from NIT Raipur, and all of you are globally connected through Wi-Fi, or that means a media. Same like as our brain, inside that neuron is there, both the sides, and that neuron having a capability to give the information to the other part. If I will stop my talk, then you cannot able to hear anything from my side. Same thing. If one side of the neuron is able to stop functioning, the other side will not get any response. And that's why the problem arises. When I was in my last service at NEHU, Northeastern Hill University, then I faced a lot of problem about that problem, how this problem can be treatable. We went to various doctors, we went to various clinics, we went to various hospitals and asked, sir, what is the solution can come out from your side to treat the Parkinson subject? And that's why we form a plan or we make a team, and that team help the doctor to early detection of the Parkinson system. And that's why we have focused on the today's topic in the hilly territory, where the support system is very, very less. That all of you know. The Northeast is isolated from the other part of the country. It is a small part, 7 small states, and 1 state is in Sikkim. The total 8 states are there. We are focusing only on Meghalaya. That is, I came from Meghalaya and it was in Shillong. So it is specially focused to the Meghalaya. And consumption of the well water, that is also a very important thing for the Parkinson subject. Now, coming to the biological signal, that is called biosignal, the significance. All of you know the EEG. It is coming from the brain. Our brain, there are 2 important ions are there. One is called sodium, another is called potassium. So that sodium and potassium, when it will be exchanged together by intercellular and extracellular activity, then some signal will come out. That signal is called as an EEG because of the ion exchange. All of you know, if ion exchange taking place, some electric potential generates. When the electric potential generates, then some sort of signal will come out. And that signal is coming like as an EEG signal. Why it is important for Parkinson's subject? Because it is an important because it is detection is a cognitive decline. Second is natural event of study is real time because you are getting the real time signal. EEG is a real time signal. Then some indicator are spontaneous which is coming on in the background. So these are the basic thing, and that's why this EEG plays a very vital role to detection of the Parkinson problem. Now coming to the EMG, that is electromyogram. Why it is important? Why the EMG is important for Parkinson? It is important because of the different type of motor function. You know motor function? Because our brain having the motor function, they are controlling our tremor. Tremor means the shaking. There is a shaking in hand, there is a shaking in lip, there is a shaking. So that's all time kind of tremor is not Parkinson tremor. But Parkinson patient having the tremor. It is very important concept. If somebody having tremor in hand, you cannot tell that he or she is suffering the Parkinson. But the Parkinson having the tremor, and that tremor is detected as a tremor identification device that I developed in my lab, tremor identification device, and that was got also patented. Now, second is bradykinesia, rigidity, postural instability. If you ask the patient to stand up for 2-3 minutes, they cannot hold it properly. They cannot hold the thing properly. And their spinal cord is little bit of towards the downwards. So that means the spinal cord having a problem due to the muscle rigidity and the stiffness. This is a very, very important task for the EMG detection. And for these things, I choose this topic. EMG plays a very vital role for detection of the Parkinson problem. And it detects the mechanism for the muscle weakness and the gait problem. Gait, all of you know, gait means your walking pattern. That means one step left side, then next step right, then again left, again right. That is the sequential way. That's why we, as human subject, normal human, normal any living organism can walk properly. If our both the leg will come forward, we cannot walk. First left, then right, then left, then right, or first right, then left, then right. So this is a pattern, and this pattern is a gait pattern. So I did 2 projects. One is the Parkinson disease detection system. Another one is the gait. How the gait is important parameter for Parkinson's disease detection system. Now, when I mix up these 2, that means these two correlation, that is EEG and EMG correlation for the Parkinson disease, that usually focus. One is brain, I already told you, and another one is muscle. That means these two things are closely interlinked with each other. When these two things closely interlinked with each other, then they detect the Parkinson problem, and that can be one of the solution for the diagnostic tool determination system. And this is one of the valid justification of the Parkinson when these two correlate with each other. One is EEG and EMG. Now, coming to the real field, what are the stages of the Parkinson? There are different types of stages are there. If you go to the doctor, they will identify the stages. Mostly we are focusing on stage 1 and stage 1.5. That is unilateral defects and unilateral axial implication. There are a lot of other effects also, but in this study, we are focusing on stage 1 and stage 1.5. Why? Because when we are measuring this stage 1 and stage 1.5, there are two types of scales are there. One is called the Gigantic Depression Scale, that is called GDS. Another one is the Mini Mental State Examination, that is called MMESE. So what are there? So there are 15 questionnaire points are there, and based on these things, you have to justify. 0 to 4 is normal, 5 to 8 is mild depression, then 9 to 11 is moderate depression, so on and so forth. There are a lot of scales out there, and based on the scale, you have to identify that the subject is under which scale. And for GDS scale only cannot determine that the patient having how much level of Parkinson unless and until you complete the total procedure of MMSE. So MMSE having the 30-point scale because it is a wide variation of scale. And that variation of scale will determine that which level of Parkinson patient you are having. Then another scale is there that is called FSS, that is Fatigue Severity Scale. And there are 9 points. 1 to 7 points is very, very important. And different 9 statements you have to ask. You have to examine. And based on the examination, before proceed for the examination, it is very important that demographic data you have to collect. So for this study, we have collected the data of age between 50 to 75 because most of the literature review and whatever the study that I have done, so I found the Parkinson is coming after age of 45. So 50 to 75 is the age that we have targeted for this particular study. Male and female, both the targets and the subjects are there. Weight is slightly 45 to 60 kg. More than that, that is also considerable. There are other things are also there. That is family history of Parkinson, yes, no. Their diet history, their brain injury is having or not, smoking. There are a lot of things are there. Even the depression of his depression history, stress, anxiety is also related with the Parkinson's. That we have to ask. That is the demographic data. And after demographic data, when we collect it, then we go for the first statistics. That is called ANOVA. All of you know the ANOVA testing. That is called the analysis of variance. And for these things, we have used the Origin 8 software. That Origin 8 software, by using, we make a comparison of the different parameter. I told you that only MMSE, only GDS, only FFS cannot tell you the actual identification of the Parkinson patient. So MMSE also we have tested, GDS also we have tested, FSS also we have tested, grip strength, SpO2, all parameter we have tested. And after the test, we did the Turkey test also. All the phenomena are there in Origin software. And if you go for the SPSS, that is also there. So different types of parameter we have targeted and we have examined, and these are the results. And after that, homogeneity also test was done. This once the test has been done in the Origin platform of subjects, then we plot it of the different angles. One is the grip strength, another one is the depression scale. You can find it that the depression scale for the control is very less but in comparison to the Parkinson is very high. In the similar case, in the different case, for the grip strength, it is better than the Parkinson subject. That means the grip means their hand is always shaking, tremor is always there. You have to measure the EMG signal. Then you can find it out that how much is the voltage is there. And accordingly, one can find out that the PD, that is for Parkinson disease patient cases, this grip strength less, very less. And if you compare the other two states, that is called fatigue severity score and the mini mental state score, that you can find it out that the control is much more than the mini mental state is high, that is called MMSE. But for the fatigue, it is very less because Parkinson subject having the high level of fatigue. Now coming to the SpO2, that is oxygen saturation in the blood, and then another graph, we can make the comparison of the all factors together. All five factors that we have explained, that FSS, MMSE, GDS, SpO2 and grip strength. These all five factors, when we plot together in a common chart, then it will be find it out that this chart will give you the actual outcome, what is the series is coming. Now you can say the highest level that is showing the violet color, that is called grip strength. So grip strength is very, very means important factor for the Parkinson patient because the hand is always tremoring. Even though the less the face, when I did the image processing for the Parkinson patient, the lip, then we find it out that the lip is always jumping. That means we plot one marker in the lip and we found in the camera that the lip is always always there is a movement. It is not a normal person. So that means this kind of shaking is there. So what we learn from the first part, that is the conclusion one. There are three parts are there in my talk. That is the part one we have completed. That means what we learned, the homogeneity of the test variance we have learned, then Turkey test we have done, then fit statistics we have measured, and we have found it out, the MMSE, GDS, FFS, SpO2 and grip strength. That give you a short understanding that the patient or subject is suffering a little amount of Parkinson subject. Okay, no problem. So first conclusion we made. Now second part of our study is coming to that, the sample size. I told you that the study is focused on Northeast, special focus to the Meghalaya. We have targeted population of 1 lakh, and this is the calculation of the sample size. From this sample size, you can able to find it out in the total population as per the Northeast Council. The reference is also given. From that, our sample size is 138. So based on the 138, we participated in different platform of the Shillong and Guwahati. And then we find it out, in the third slide, I show you, there are two stages. One stage is stage 1, another stage is stage 1.5. So these are the two things with the upper limb tremor and unilateral damage. These two sides we are focusing. And our age limit already I have discussed with the 50 to 75. But exclusion criteria is also there. We are not considering other stages, and we are not considering the age less than 50, above 75. And there are a lot of other things, those who are having the metallic implant, somebody having the knee or the knee implant, hip implant, or other part of the implant, that we are not considering for this study. That means exclusion and inclusion criteria is very important for any kind of study. Now, these are the basic apparatus that we have used for your basic understanding. This is bioamplifier that we have used for the AD instrument from Australia. This is one of the renowned company for the bioelectronics. So we use the PowerLab 26T, and this is basically focused to the different channels, because next part we will measure the bioelectric signal, that is called EEG and EMG. For these things, this kind of equipment is very important, and pulse oximeter also connected, dynamometer also connected. So this type of equipment is very important. In one console, all type of recording can come together. Now coming to the biological, when we are collecting data, then different types of electrodes that you have connected to different parts of the body, and that is having different functions. Lead 1, lead 2, lead 2, lead 2, then ground, different types of electrodes, their position and their functions. Now coming to the subject, these are the basic subjects that we have collected the data for EEG and the SpO2 collection. Because when we collecting the data of EEG, you cannot take the data for EMG. So basic protocol is EEG and SpO2 you can collect together, but EMG when you collect, you cannot collect the EEG, because EEG is a very, very systematic signal, nonlinear signal and chaotic in nature. So that's why you don't use any other thing when you collected the EEG signal. This is basic waveform that we have displayed. First one is the SpO2, second is the frontal EEG. We have basically focused on the two channel. One is the frontal, one is the temporal. These are the normal subject, that is called healthy subject, the EEG pattern of the brain. From these things, you cannot able to find it out that where is the problem and is there any problem or not. That I'm coming later. And this is the Parkinson's subject. So little bit of knowledge you can get it from the waveform. If you can compare with this to normal, this is normal, and this is some kind of problem is there. SpO2 also problem, frontal EEG also problem, temporal EEG also problem. So these are having different problems are there. So for EMG also, what are the different leads we have connected? What are the muscle location? And as well as what are the functions are there? So based on these things, we concentrate for the EMG and grip strength. So first one was the EEG and SpO2. Second one is the EMG and grip strength. So don't mix up with two. So both the signal coming together, grip strength and EMG also electrode connected to the muscle. We have to identify the muscle first, and then you have to collect the data by using the hand dynamometer. And then coming to the EMG graph, the first is the grip strength graph, second one is the muscle 1, muscle 2. There are two muscle is identified. And then if you connect the healthy subject and Parkinson, this is for PD and this is for healthy. So then you can obviously find it out what is the problem. But from here, it is very difficult to find it out what is the actual problem is there from this graph. Now coming to the different activity, if you can see the two plots, that is the EEG corresponding plot with the normal with the Parkinson, then you can see that the Parkinson level is very, very less. That means their brain function is fantastic, no problem. But due to the less activity of the substantia nigra region of the brain, their activity, that means the signal strength is very less. They cannot able to transmit the signal from one end to another end. If suppose if there is a loss in the network, you cannot able to hear what I am talking, because you are globally connected through wireless media. So same thing like here, if substantia nigra region is less amount of dopamine, is not transferring the biogenic amine properly, then what is the problem is there, that their strength, signal strength amplitude is very, very less compared with the normal or healthy subject. Same like as our EMG problem. For EMG, you can see it is a very, very high. Because why? Because it is an uncontrollable signal. The signal cannot be controlled. Their signal is basically random in nature because they cannot hold it properly, they cannot flex it properly. Their flexion and extension is not proper. So their muscle movement is not proper. Contraction, relaxation is not proper. So everything is totally disrupted. So that's why this kind of thing is coming. Now coming to the signal processing part of my topic, you got the EMG, you got the ECG, EEG. Now there is a cutoff frequency is there 1 to 50 hertz and sampling frequency is 240 hertz. And EMG also 5 to 500 hertz and sampling frequency is 1000 hertz. Then there are some feature extraction. What we measure? We measure a lot of things. For EEG, there are 8-9 parameters we have measured. For EMG, we have measured also 7-8 parameters we have measured. And from this study, before proceed for study, we also did the AI, that is called classification. That is called artificial intelligence. and artificial neural network. And that also required to train the signal. So first, we have to put the normal signal into the system. Then we give the real-time signal, and we already make our GUI, own GUI, and that GUI will give you, if somebody is giving me the signal, then I can tell you that your signal is Parkinson signal or normal signal, or is there any problem in the signal or not? And that we have already met, and that was also copyrighted in my name. So when the EEG and EMG features are there, then we train the data and we minimize different types of parameter, and the classifier will tell you at the end of the day that the subject is having any Parkinson or the subject is having without Parkinson. So that has to be identified at the end of the day. So what we did, the first we did experiment, we made the Lyapunov exponent. The Lyapunov exponent is the procedure. It is a very, very basic physics. Those who are from physics, so they know what is Lyapunov exponent. You know the attractor. Attractor means in the nonlinear dynamics, there is a freely movement attractors are there. That attractors will tell you that how much is deviations are there from normal to abnormal. That deviations you have to identify. And from identification, you have to make the Lyapunov extent, because it is the whole universe. In that whole universe, you have to make one attractor because it is chaotic in nature. The signal is chaotic in nature. So that's why in the control subject versus Parkinson subject for temporal and control subject for the frontal and Parkinson, if you can make and if you can give the result from the graph, we understand, we did the things in the MATLAB, and from these things, we find it out that how much is the deviation. If you can see, the deviation is the temporal role for the Lyapunov exponent for normal, and for the PD is slightly high, and for inverse is slightly decrease. So that means it is very, very obvious that for the normal is cases and for inverse Lyapunov exponent, obviously it should be decreased than the normal cases. And you have to identify that if the Lyapunov exponent is high, then their brain condition is closely interlinked with each other. That means their brain is functioning properly. But if there is a problem in the Lyapunov exponent, that means their brain is not functioning properly. They're having a neuronal damage. And if you can make the plots, that Lyapunov exponent for the healthy subject versus the Parkinson patient, you could find it out. The box plot will give you the information, what is the actual significance of the graph. Then we did the second experiment that is called autocorrelation. Autocorrelation means the correlation between the brain neurons that you have to identify. That control subject, the frontal brain, and the Parkinson brain for the frontal brain, you can identify. Then similarly, we did for temporal and temporal for the Parkinson. And from that, we are identifying the maximum voluntary contraction, that is called percentage of MVC. And percentage of MVC for the healthy subject is 81 and Parkinson is 54. That means it is very, very less. That means it will identify the grip strength that we have identified. The grip strength is very, very less for the Parkinson subject. That means they cannot hold the ball properly. They cannot hold the glass properly. Even though any moment of time, it can fall down. So the grip strength, the maximum voluntary contraction is very, very less. So you have to identify the percentage of MVC. Now, if you can compare the different aspects, like as the standard deviation, variance, mean square root, waveform, power, frequency, different parameters, if you can find out, you will find out that there are 4 parameters, like as our mean root square, that is called RMS, that is called, another is called the power, that the healthy subject is very, very higher than the Parkinson subject. That means it will give some variance in the time domain and the frequency domain features of the different hand muscle. So that identification will give you the information that the standard deviation, the mean root square RMS wavelength having the information to give you the actual field, how much is the deviation from the Parkinson subject to the healthy subject. Now, if you can make the comparison between the EMG signal of the different deviation that I plotted here, it is the graphical representation. You can able to find it out. The maximum root square and the modified median frequency, that is very, very less for the Parkinson's subject with comparison to the healthy subject. Healthy subject is represented as the brown color and the Parkinson is represented as the blue color. So these two parameters, apart from that, the power, wavelength are very, very comparable phenomena apart from these two. Now, all the data, when if you are in your hand, then you move forward to the artificial neural network. An artificial neural network that we have made, that is called feed-forward network. And backpropagation is also there, because if somebody having a real-time signal of EEG and EMG, if you can feed to the system will identify the subject is Parkinson or not. And I told you that GUI that I have already developed, and it is also copyrighted. So I have the GUI, and that GUI will give you the instruction immediately for the neurologist that the patient is suffering Parkinson or not. So this artificial neural network, when we are working, that require three important things. One is called training, validation, and testing. Because training phase is very important. If you don't know what is the features, if you don't feed the features inside the system cannot validate you. System cannot test you. So that's why the training phase is very, very important than validation and testing phase rather than. And similarly, the backpropagation network, backlining propagation algorithm is also very important for the EEG, EMG purposes. Different transfer function we have used and basic statistics that we have placed, it is for the one training a function. So for these things, we did the EEG, we did the EMG, and we did the both together, EEG and EMG. So that means that one is for single, another is for single, and last one we make for the correlation between EEG and EMG for Parkinson's. So it will give you the close interaction. The second is called the second training function. And for that thing, we made the different results. And last, we made the main important part, that is the train function. That is the most important training function that we have used. And we did this experiment and we got the best result from this part. When we did the EEG and EMG in the red color that I have highlighted, this will give you the actual result. And that number of subject and that number of result will give you the actual R value. If you can find it out, it is very close to 1. That means this transfer function or training function will give you the most important criteria or characteristics when we use both together for EEG and EMG especially. Now coming to the overall comparison, because there are 3 different training functions that I have used so far. Now you can comparison between 2, then you can find it out that the TrainLM has given the best result. It is 0.9972 with a classification rate of 98.8%. That means accuracy point. And the number of inputs we have used 12. So we did a lot of efforts for the training function on the TrainLM for detection of the EEG and EMG. If we comparison these two with the other, that is the last chart, then the single for EEG and EMG, and if you compare with the correlate with the together EEG and EMG, then the TrainLM function will give you the accurate result. It is very close to 1 for the R value. And that will give the special significance that the patient is suffering, the Parkinson patient. Now coming to the conclusion 2, what we learned from this chapter. This chapter will give you the 2 important factors. One is called the Lyapunov exponent, that is the nonlinear dynamics. That I did the very, very high for the temporal brain region and frontal also. Then second part, we learned the autocorrelation function. And third part, that is called Shannon entropy, that Parkinson's subject is very, very the neutral complexity and higher value of the percentage MVC that I told you for the grip strength for percentage MVC detection is very less for the Parkinson disease. It is the conclusion 2. And apart from these things, what we learned, that is the ANN, that is artificial neural network, if you can do for the classification purposes, the TrainLM function has given the 98.8% of significance for EEG and EMG correlation together, and it will give you the best practice for detection of the Parkinson disease of the classification rate. Now coming to the third part of my talk, that is called the radiological interpretation. We also collected the MRI signal from hospital after completion of the ethical and the collaboration of the nearby NIGRIMS and as well as the government hospital in the Assam. And we find out that the MRI signal will also give you the significance of the less amount of dopamine deposition in the brain. And also it is a very important biomarker for informing the diagnosis, tracking, decretion, and as well as the symptoms detection. So the picture that I am placing over here, in the brain, there are two lobes that there. It's the substantia nigra region, and that substantia nigra region, if the less amount of dopamine level is there, from this picture, that identifying that the how much is the dopamine depositions are there, and this is the dopamine depositions of the normal, and this is the normal cases, and this is the PD cases. So that means the PD cases, if you can see the normal, it is a bean shape, and when you go for the Parkinson subject, it is a simple circular shape. That means bean shape is totally changed to the circular shape due to the less amount of dopamine in the substantia nigra region. It is very, very crucial factor for determining the Parkinson subject, and it is the MRI. Then coming to our last part, that is called GUI. I told you that the GUI has the capability to give you the all information together, your MRI signal, your EMG signal, your EEG signal, your normal history, that is called the demographic profile, then a lot of other things, that is the mean, variance, standard deviation, mean root square, waveform length, different type of things. Though when you go together, if you give the instruction, you will give the value, and they will determine that what type of the identification factors are there, and how much is the Parkinson level is associated for the subjects. So from here, we find it out that it is the stage 1 of PD. If somebody having stage 2, stage 3, stage 4, that means this type of software, if you can give to the any hospital, then doctor can easily find it out, or technician can easily find it out that, okay, in a fraction of a second, that, okay, somebody having the Parkinson patient. But in the very naked eye, if somebody having the tremor, it is very difficult to find it out that what type of problem is there. If the EEG is also uncontrollable, but the EMG is fully functional, that is also not considered as a Parkinson patient. But the other factors, like as our xenon entropy or percentage MVC, so that is Lyapunov exponent, autocorrelation, and this will give you an overall impression of the Parkinson patient. So what you learn from the conclusion 3, that is the third part, that is the neurological part of our, that is special focus to the radiology. So this is basically focused to the area that is called, that area that I told you, that bean shape is very, very small in size for the Parkinson patient, and clinician can ever monitor, and from there they can detect and they can note it out that the substantia nigra region, the zone is very, very less. So you can share that the final conclusion is that it is a very novel tool to detection of the Parkinson problem. So what is the summary of the whole research? Because I presented the 3 different aspects of the Parkinson patient. The whole summary is represented in the 3 different aspects: demographic profile, MMSE, GDS, FSS, and grip strength is the first. Second, we have find it out the EEG and EMG. Third one, we have find it out the Lyapunov exponent, autocorrelation, and finally we come to the conclusion that the GUI will give you all 10 parameters or 12 parameters together to give you the actual basics of the level of the Parkinson patient. So that's why it is useful for this GUI. The final statement that I have wrote, the model was designed using MATLAB graphical user interface GUI, is a single window for early diagnosis using biological, radiological intervention to PD. So with these few words, this is a few major references that I have used. With these few words, I am stopping here. If you have any question, you can ask me. Thank you.
Any questions, please? Any questions from the audience?
Ashok Behra ji, you can ask. I have unmuted. Allow access to
हाँ जी सर,
everyone.
हाँ जी सर, हाँ जी सर, नमस्कार सर. हेलो, am I audible?
Yeah,
Yes, yes, you are audible.
yeah,
Sir, my
yeah,
question is that in dopamine, basically, sorry, in Parkinson, basically, dopamine is less.
yeah,
So the signals what we are getting, basically what image you shown, right? No, that
yeah.
are that is dopamine you are saying? That EMG?
Sir, I'm not getting your question. Little bit of. Could you please repeat once, because I'm not getting your sound properly.
Yes, sir. Just a minute, sir. Now I think it's clear, sir.
Yeah, yeah. Please.
Yes, sir. My question is that in Parkinson, dopamine level is below the normal,
Yeah,
right?
yeah. Obviously, yeah.
So it may be any region. You are saying that due to taking well water
It
in
may be any
Meghalaya,
reason. Yeah, yeah,
yeah,
yeah.
in
Hmm.
Meghalaya, but basically the heavy minerals used to deposit in the brain. How they cross BBB, that's a magical thing or what we don't know.
Yeah, yeah,
Okay, so thing is that what makes the image to be come in the EMG because dopamine level is decreased. So what ions that are that showing the image of EMG? Can you
yeah,
please explain what is
yeah,
happening to the your extracellular fluid or intracellular fluid
yeah,
or what
yeah,
the
yeah,
minerals are there? What
yeah,
is that exactly? And
yeah.
what work what you are measuring or what you think that?
So basically, when the experiment has been considered that less amount of dopamine in the brain, that doctor used to test it. That is the basic phenomena that their dopamine level is less. Now, after the determination of dopamine level is less, now you can focus to the person having the Parkinson or not. That means first phase is carried out by the neurologist. They have to treat that dopamine level is less. That dopamine level is less due to the many reasons. So I am not going to the details. So there is a ion exchange is there due to the difficulties transformer transmission. But after confirmation side from the neurologist, so once the dopamine level is less, it is confirmed, then our study will be start, because once the dopamine level is less, first indication is that the person or the subject may have a chance to prone the Parkinson. Now, from that point, we have started our study. When the neurologist confirmed that, okay, the person suffering the Parkinson, okay, that's fine, no problem. If the person is coming first time to the doctor, the dopamine level is less. Now they have sent it or requested us, okay, you can carry forward your research. He or she may prone to the Parkinson in near future. That is for the early detection of the Parkinson disease.
Sir, but the EMG, the signals what it is coming that are
Yeah.
due to what? What signals that are?
EMG is basically the all of you know that is the muscle activity. That is the electromyogram. Okay.
Yeah,
So
okay.
basically, when you connect the electrode to your muscle, it will give you the muscle contraction and relaxation. If somebody having a contraction, relaxation is very nice. But somebody having a problem, they cannot able to hold it properly. They cannot able to contract properly. Their flexion, extension is not good. So that their what problem? The muscle is always in rigid position. So that what happened? They cannot fold it properly. They cannot hold it properly, or they cannot even the relax properly. So the always their voltage level is higher than the normal level. That's why I show you for the EMG pattern, always Parkinson patient EMG signal, their amplitude is basically higher than the normal level. Although for EEG, the voltage level is less always in Parkinson compared with the normal subject, healthy subject.
Okay, fine, sir. Fine.
Yeah.
So what work you did basically? You make a instrument or what to measure that?
First,
I'm not understand that.
we did lot of things. Once the subject is confirmed by the neurologist that the subject is the Parkinson or maybe Parkinson, we started our journey by using our own apparatus that was also got patented. The GUI also got copyrighted. Then we feed all the phenomena, first taking the EEG, EMG. Then we make our own prototype for the tremor identification device. We feed all the data to our own GUI, and GUI will give you the stage. Okay, the patient is Parkinson confirmed, level 1 Parkinson, level 2 Parkinson, risk factor, many things is coming out from this study. It is a very big study. Yeah.
Okay, sir. Thank you.
Yeah, thank you.
Is there any question? We will be happy to have it if you have.
If somebody who were interested, so obviously I can help you in this particular field, because I did a lot of efforts. So I did a lot of work in the field of the Parkinson hardware designing, software designing, and if you are really interested, you can contact me. We can do the joint work, no problem at all. Or if a student need any help, they can ask me any point of time. I will free to help you.
Sir, I think nobody is interested and all are busy in lunch. I think they have walked away with that.
Okay, sir. We proceed with felicitation. Here, sir.
Many thanks, Dr. Paul, for an engaging and informative session. Your
Okay,
discussion,
thank you, Dr. Dhiraj. Yeah.
your discussion on the role of EEG and EMG in Parkinson's disease detection system brought forward exciting perspectives and practical applications. You have a very clear explanation of all the techniques and their clinical relevance, which added a great value to the lecture. And I think we got a very good information regarding our disease in nowadays. So thanks a lot, sir. Now I will
Thank
request
you.
uh, Dr. Yumnesh to present a virtual memento to the sir for his contribution to this FDP.
And Dr. Gaurav is online?
Yes, sir. Yes, sir. Yes, sir.
Okay,
Thank
If
you.
so
Dr.
Dr.
Gaurav
Gaurav,
is online, then I will request Dr. Gaurav to present as a token of gratitude to.
okay, so before proceed for token of appreciation, Dr. Gaurav, recently I joined as NIT Raipur, and Gaurav is my junior. In the same lab we did the PhD from IIT BHU. So I know Dr. Gaurav in the very long run. So in future, if any type of collaborative work is required with the NIT Raipur, definitely I am ready to help.
Thank you.
No
Thank you
problem.
so much, sir, for your blessing,
Yeah,
your kindness, and your guidance, sir.
So
And thank
Sudeep
you.
sir, there is a message in chat box. Many
Okay.
things are new to us, but it was quite informative and detailed session. Thank you, sir.
yeah, Dr. Ubnesh. Yeah, thank you.
It was written by some Divya, ma'am is Dr. Divya. So they said that many things are new to us, but it was quite informative and detailed session. Thank
Sure,
you. They
sure,
said.
sure, sure.
Okay.
Thank you, Dr. Ubnesh.
Gaurav sir, please
Yes.
felicitate
Yes, sir.
sir.
Yeah. Yes, sir. Yes, sir. Okay. Sir, thank you so much, sir, once again
Thank you.
for accepting our invitation and conducting such an informative, engaging, and interactive session. So kindly accept this e-memento, sir,
Thank
from
you. Thank
on
you.
behalf of our organizing committee members, sir.
Thank
Thank
you.
you.
Thank you, Dr. Gaurav. Thank you. Yeah.
Thank you, sir. Once again, Dr. Yuvresh, shall I proceed with the new
Ah,
speaker?
sir, sure, sir, sure, sir, sure, sir.
Okay, thank you, sir. We are now pleased to invite Dr. S. Rakshit from Department of Chemistry, MNIT Allahabad, a distinguished expert in the biosensing applications in medicine and diagnostics. Dr. Rakshit did his bachelor's, master's, and PhD all from Jadavpur University, Kolkata. Before joining MNIT Allahabad, he was a Marie Curie Fellow at Universidad de Castilla Mancha, UCLM, and a National Postdoctoral Fellow at IIT Mumbai. His current research interest focuses on design and synthesis of anti-cancer drugs in fluorescent levels for cancer cells, designing of fluorophores for probing amyloid fibrils, synthesis of AIE active molecules for biosensing and bioimaging, drug protein and drug DNA interaction. We have a privilege that he will be speaking on the topic molecule aggregates for biosensing and imaging. Dear Rakshit sir, we are honored to have. So please proceed with your session. Dr. Rakshit, am I audible, Dr. Rakshit?
Give us a moment.
Yes. Yes, yes, thanks. Am I audible now?
Yes,
Am I
Dr.
audible now?
Audible.
Yes,
Yes,
please proceed.
yes, yes. Hello, everyone. So, thank you very much, organizers, Gaurav ji, Yuvnesh, Dheeraj ji, Saurav, for giving me this opportunity to give a lecture on my research topic in this FDP. Actually, let me share my screen first. How can I share my screen? Share, okay. Entire screen. Are my slides visible? Hello.
Yes, sir. Yes, sir.
Okay, okay, thank you. So I'll be talking about this molecular aggregates for biosensing and bioimaging, understanding the mechanism and role of molecular aggregation. The thing is that since engineering faculties, most of the faculties involved here are engineering faculty from coming from engineering backgrounds and all. They normally generally works on image processing and all these things. So our work is previous to that. To get a, I mean, when you are talking about cell imaging or sensing some biomolecules within the cells and all these things, you need some probes or some very good material or molecules which can actually, which are actually fluorescent or something. Normally, fluorescent is the most non-invasive technique in this case. So I work on fluorescence. So here we work in the first step of this. I mean, before doing the image processing and all these things, we try to develop some very good materials which can actually, uh, uh, I mean, image the cancer cells or biomolecules in the cell itself. Let's start with very basic thing before we say I mean let me tell you this that maybe most of the people know this term, but rather they don't know how, what are the processes involved and all these things. So here, the thing is that the term fluorescence is totally related to electronic transition in molecules and materials. Now, in here, this is called a Jablonski diagram. Now, here I have given the electronic transition, different transition levels of a molecule. In case molecule, the ground singlet state, first excited singlet state, second excited singlet state, all the singlet states are there. And in case of material like quantum dots, perovskite, those are also very fluorescent materials. There, actually, the normal valence band and conduction band is there, and the hot hole and hot electron, all these are involved. Now let's concentrate on this fluorescence. So fluorescence, basically what happens that this, upon excitation, the ground state, the electrons residing in the ground state, they get excited and they just go to the next or next to next excited state. Now, when they go there, it's you can say this is not the normal state. This is an excited state. Now, like us also, when we get angry, we can't get angry until infinity. We get angry for some time and then we come to our ground state. This is the same case also. When you excite a molecule, that electron goes to the excited state and then they reside there for some time. The time is very low. After that, they lose that excess energy and come to the ground state. Now, while coming to the ground state, they lose that excess energy. Now, they lose this excess energy via two processes. One, it can be a non-radiative process, that means via heat or something, or it's a radiative process. Now, the radiative process, we call it fluorescence. And the timing in which the molecule reside at the excited state is basically around some nanosecond or something, 100 to point, zero point 0.1 to 100 nanosecond. And here there's another thing. So in some molecules, in singlet excited state, with singlet excited state, some triplet excited state is also there. Although singlet to triplet state, this conversion is not allowed. It's a spin forward transition. But still, in some cases, very few cases, they actually the crossover actually takes place, and the electron from singlet excited state comes to the triplet excited state, and then it loses its energy from triplet excited state to ground state. Here also, it can lose its energy in radiative way or non-radiative way. The non-radiative pathway we are not interested about, right? Because that is they're losing the excess energy via heat. But in case of excited state, it now, since this crossover takes place and then it coming to the ground state, there's a time lag is there, and when this time lag is there, then we call it phosphorescence. So basically the time range of phosphorescence lies between like 10 second to 1 microsecond, like this only. So you can understand. So this is all the this is all in all are in this Jablonski diagram. So this is basically fluorescence if you think of it. Now, there are conventional molecules. If you go, if you if you find Google Google for Google search for any fluorescent molecule, these three are the molecules which comes up the most comes up in the search. That is rhodamine B, Nile red, and fluorescent. They are conventional fluorescent molecules. Rhodamine B used for different imaging membranes or cytoplasm. Nile red is basically very famous to stain cell membranes, and fluorescein also that for imaging cytoplasm. Fluorescein is also very popular. Used to be, actually not right now. It used to be until 2000 2005. You can see hundreds of papers with this kind of they synthesize some derivatives of this type of molecules, and they get imaging, or by fluorescein Nile red or rhodamine B itself, they get good fluorescence imaging and all these things. But the thing is that with this conventional molecule, there are some problems, serious problems were actually coming in the way. The first one is aggregation cost quenching. Now, what is aggregation cost quenching? Now, these molecule, these conventional fluorescent molecules works very good in the concentration range of micromolar concentration range, right? Like within 10 micromolar, it gives you fantastic result. But the problem, if you get a slightly increased concentration, sometimes you have to use some increased concentration. Then what happens? These molecules tend to aggregate. And when they aggregate, what happens? The pi-pi stacking comes up. And when pi-pi stacking comes up, they lose its energy. And they lose its energy, they lose its emission. And what happens? You will no longer be able to image the cells or anything. So this phenomena is called aggregation cost quenching. And another thing is photo bleaching. The most conventional dyes are for, like, if you have to do some imaging or something, what you need to do is you have to expose those molecules to light for a long time. It's not like just 1 second or 2 second. No, it's not and I used to work in laser. So the thing is that when you are working with laser is very high concentrated light, high energy light. So with high energy light, they photo bleach just very rapidly. I mean, within 10, 20 shots of light pulse, and your molecule is gone. So we needed, I mean, scientists were looking for molecules which can actually stay strong in front of those. I mean, in presence of light and all these things. Actually, the starting research of this quantum dot and perovskite started with this idea that to stop this photo bleaching, we need to look for materials which are more stable under light, and that's how quantum dots actually the research on quantum dots started. And also this poor water solubility and low signal to noise ratio, and in and short excitation emission wavelength range and all these things. And then what happens in 2001? In 2001, Professor B.Z. Tang revolutionized this idea of imaging or of this, I mean, conventional fluorescent molecules. What he did, this is the first example. This TPE is called tetraphenylethene. This is the first of its kind where it you can say it's a propeller-like shape, and at the same time, the cool part is that it's just floating around in solution, and it does not emit light because it always like, I mean, because this phenyl rings you see, they usually rotate very freely. That free rotation drains energy through non-radiative pathways. But what actually comes up, and this is in pure solvent, I mean, good solvent, means in a solvent, because you need to solubilize the fluorescent probe. So when you solubilize the fluorescent probe in a very good solvent like DMF, THF, or hexane or anything, they rotate very freely, and when they rotate very freely, they normally lose that energy via this rotation, and this non-radiative pathways opens up. But what he did, he added some water and all. Then what happened? The molecules, the solubility comes up, and due to poor solubility, the molecules tends to aggregate, and when they aggregate, the rotations, the free rotations got blocked, and when they got blocked, they got blocked. Then the intensity of the emission intensity, I mean, just shoot up, and this is kind of very important kind of molecules. The conventional dye molecules, the structures are different. Here also, here the structure is a little bit different. Here we call it AIJ, or more important term is fluorogenic molecule, which are non-fluorescent in good solvent. I mean, which solvent is purely soluble, and they are very much fluorescent in good solvent, poor solvent, where the solubility is very low. And look at look at the second molecule here. This second molecule is called THBA. It's a basically derivative of TPE. And here also the here you can see this there are some bendable parts, sort of like flexible arms. No, now when you stop this flexible vibration of this molecule, you can also increase the emission intensity. So in the first molecule, we are restricting the intermolecular rotation. Here we are restricting the intermolecular vibration. So RIR and RIV, these are the two main mechanisms to increase the fluorescence of a fluorogenic molecule. Okay. Okay. Now let's come to, okay, this is the aggregation induced emission. These are very what can I say? I mean, very well-known compounds where we can see the AIE effect, and which can be used for fluorescence imaging and fluorescence sensing. I mean, basically in cells. Okay, so design principle for ratiometric AI-gen probes. So what I thought, actually giving you a lots of example. I mean, instead of telling you a lots of example, rather concentrate, because it's a FDP. Rather concentrate on the how these kind of probes are being designed, and this is okay. This is the first uh, scheme by which one can develop or design a ratiometric AI-gen probe. So there are basically three strategies. I'm telling you one by one. So let's focus on the first one. The idea is pretty simple. You introduce a second signal into your system that does not respond to the target, and it just stays constant and acts like a reference. So imagine like this: you have a one part of the probe that reacts with the target is present, and it changes its intensity or color, while the other part is does not. I mean, it's totally unaffected. So the reference signal gets stays steady, and you can compare it with the change in signal. By the way, am I audible or something? Audible or not? Because I can't see any. I can't hear
You go
any.
ahead, sir. Go ahead.
Oh, okay. So, so one is there, while the other part just sits there unaffected. Because the reference signal stays steady, you can compare it against the changing signal and get a more reliable readout. So one straightforward way to make this happen is by physically combining them both the parts actually. So the responsive one and the reference one into a single probe. That way, even if there are changes in the surrounding environment like pH or polarity, the reference stays stable. This setup helps correct for those kinds of variation automatically. Now, this actually improves the accuracy and repeatability of the signal. I mean, it actually increases the signal basically. Now, this is one way to do it, and another way to do it is slightly more dynamic. That instead of having a static reference signal, this one uses two signals that are actually linked together. So they basically both changes, but in opposite direction. So maybe one goes down, one goes up. So when one signal increases, other signal decreases. That change in ratio gives you a readout or gives you a good output, what you need. So one way to pull this off is by building an AI-gen based composite probe that has multiple signal generating components. So when the target binds, right, either through physical absorption or through like chemical interaction or something, it triggers process like energy transfer, electron transfer, which shift the signal in a coordinated and reversible way. And there's also a kind of clever trick in this also. So you can design AI-gen probes that only become active when a particular stimulus is present, and in this case the target actually switches off one signal and switches on a new one. So you just don't get a change in intensity, you get a clear shift of one signal to another, and which is super useful for ratiometric detection. So this, I mean, we are designing this kind of AI-gen probes, keeping in mind we have to sense the molecule first. because there are many kind of proteins or biothiols or enzymes in the solution which we need to sense first. Then comes the imaging part and all. So we have to design it. I mean, we have to fulfill both the what can I say? We have to fulfill both the conditions, that it will sense and it will image that molecule in the cell as well. And the third one is that this is a slightly bit different strategy, that it uses two signals that both responds to the target, but they don't necessarily change in the same way. One might increase a lot while the other increase just a bit, or one might decrease a lot, another might decrease a bit. So still it's ratiometry. So with that ratio of that two signals, you can detect. But nevertheless, by comparing these three strategies, you can totally understand the second one we talk about is the most efficient one. Why? Because it is simpler, it gives a more clean signal and with less background interference, because here one goes down, one goes up. So that ratio metric study becomes more acceptable or more intense, because in the first case one is, I mean, the reference probe is not changing, but here what, both the probe is changing, one is decreasing, one is increasing, or either way. So here you always get a much better signal to noise ratio, and that's why it becomes the go-to choice, and especially for making reversible ratiometric AIGN probes. Okay. uh, okay, so now another one is uh, AIGN composite probe. Now, ratiometric fluorescent probes are actually one of the most powerful tools we have biosensing and bioimaging. Now, here's the difference. Sorry. Uh, Here, what we do in the first case, that we have to combine two or more different fluorescent dyes. In the second, uh, here ICT is called internal charge transfer. So maybe we can mix two components. It will have two components where one is showing strong ICT, where one is showing weak ICT. It's the same case, the second one. So one is the third one. The third, sorry. It seems sorry. Okay, sorry. Let's start with the AIGN composite probe. So here, the mechanical composition, mechanical combination of this probe 1 and probe 2, and they can be embedded into nanoparticles, maybe in polymer material, maybe in PMMA matrix, maybe in chitosan matrix, maybe in silica matrix. So this kind of core shell structure can happen, and also there also you can get the AIGN effect. Okay, and in case B, manipulating the aggregated and dispersed states of probes within AIE ACQ hybrid dual probe. So what happens when you increase the concentration? One gets aggregated and gives you good signal. Suppose you have a AIE probe which is red emissive, and you have a ACQ probe which is green emissive. Now in good solvent, what happens? You will only get signal from ACQ probe, because that's in, I mean, in normal cases. In good solvent, only the fluorescent molecule will give you signal. Now, when you put bad solvent, or in the solvents which these probes are not soluble, the AIE probe starts aggregating, and when it starts aggregating, it will give you the red fluorescence, and then at the same time, this ACQ probe, the green emission goes down, so that ratio metric goes up and down. This part will aggregate and disaggregate. This way, you can actually regulate the ratiometry. The second one, the third one, what is that? That a target sensitive probe. So introducing a target sensitive probe within this hybrid system. So what happens when this reference probe, I mean, doesn't react, another reference probe gets, what can I say, gets attached with the target, and that gives you maybe fluorescence, or maybe the fluorescence goes down. So suppose in here, what I showed, there's a green emission and a red emission. So initially both are present. Now this red emission can bind with the target, not the green one. So when the red one binds with the target, what happens? The intensity of fluorescence intensity of this red probe goes down. So now we have only one. So this reference probe doesn't change, the intensity doesn't change, but the fluorescence intensity of the red probe, which binds with the target, goes totally down. So now we have also a ratiometry. Okay. Okay. So and this is a kind of what can I say? Uh, the one of the smart ways to smart approach in ratiometric sensing, where this here I took it from a paper where the two fluorescent materials that glow at different wavelengths and they put them together in a polymer matrix. So when do you do that? So it's a AIGEN composite nanoprobe now. So one dye is acting as a stable reference, maybe the green one, and the red one is the basically it's basically the rhodamine probe. So this rhodamine is non-fluorescent basically. When in native state it's non-fluorescent, but when it binds with mercury, what happens? The fluorescence shoots up. So in the first, this green emission, in the starting, we have two probes on the green emission. This AIE monomer is only green. We have only green emission. Now, when you add Ag2 plus, now it's a mixture of green and orange emission, or some reddish emission. So basically, you can generate. You can generate deep orange emission, and you get mercury sensing, and it can be used in cell also. Now, okay, now let's talk about single molecule AIGEN probes for ratiometric sensing. Now, they're really now for single molecule sensing, you have to be much more sophisticated, and they are really fascinating. The idea is really fascinating, because just one molecule give up multiple emissions depending on how much of the target is present. Now, these different emissions might come from the AIGEN itself, or sometimes from an additional fluorescent group that's been built into the same molecule. Now, over the past years, what happened? The researchers have gone really clever with tuning the emission properties of agents and all this. And one very common strategy is adding donor and acceptor groups to AIE core. So one part donates the energy, and one part is accepting the energy. So beautiful shift of energy, like the Stokes shift is very high, and you get a very good signal. So another trick is to combine AIE units with traditional ACQ dyes. Similar. So once you do it, what happens that one part, I told you that this one, and okay, so another so which normally gets the ACQ dye gets quenched when aggregated, and the AIE probe gets the emission intensity increases when it's get aggregated. So this is the thing, and some key mechanisms used in these designs. These are like ICT, monomer hexamer formation. The first one, two ICT or intermolecular charge transfer, TICT, where the molecule twists, twisting induced charge transfer, where the molecule twists and changes how it emits light, and ESIPT is called excited proton transfer, internal intramolecular proton transfer or intramolecular proton transfer. Now I am working on this particular subject, AI ESIPT based AI probes. Now ESIPT based AI probes are very fascinating kind of compounds because they are very sensitive towards the surrounding. If you change slightly change in pH or slightly addition of some molecules can change the emission, a big shift. The big shift can happen, and maybe it has basically normally it has two different what can I say, two different mm, structure, two different formats. One is enol form, one is keto form. So keto form is with less, it has less energy, so it emits around in the red region or yellow region, and the enol form is of high energy, and that it actually emits around normally in all the cases basically 480 or 500. So when you take out that proton, this proton, when I'm talking about this proton, when you bind this proton or take out this proton with the pH or with the addition of any foreign molecule, what happens? This keto form starts forming. And when this keto form starts forming, there's a beautiful shift in fluorescence happens. So that 480 fluorescence peaks goes down, and this around 580 or 600, the peak around 580 or 600 goes up. So that beautiful ratiometric response you can easily get. And energy transfer process like freight, TBET, which in which where energy moves between different parts of the molecule, this can happen. So using these smart designs, now people are building a whole variety of high performance ratiometric sensors. Now, until I mean, we used to have sensors and all these things, but the thing is that you don't know exactly which will work, and even if it works, it will hold up while you are giving light or not. Now in the aggregated form, you know they are not photo bleaching easily, you know it can be destroyed easily, so it will be, and their sensing property is similar to the single molecule. So now what happens, you are guarded in all the sites. And when people are saying quantum dot based or perovskite based sensing of molecule, or I mean enzymes or biothiols or all these things, they normally what they do, they functionalize the surface of quantum dots or perovskite nanoplates or nanoparticles with the molecule which can target the target molecule. So basically, you need even if quantum in case of quantum dot or in case of perovskite, you need a molecule which actually binds with the target. So here, I mean, here I have the target molecule, but I'm aggregating the target molecule, so I don't need the quantum dot perovskite. Itself, the aggregated structure of that molecule acts as the sensing platform and imaging platform, and as well as they are very much stable. So that's why this field is gaining so much recognition right now. And while the synthesis part is getting recognized, there's a whole lot of mechanism stuff, how they are forming, how they are getting formed, how they are sensing the molecules. This is a whole branch of research is going on now. This is not in my slide, but let me tell you something. So when I'm saying this good solvent, bad solvent thing, that means when you put bad solvent, of course, the aggregated molecule is forming and the emission goes up. It's perfect. Okay, fine. But the thing is that there's also the structural deformation can stop that intensity enhancement up to a certain level. Maybe it should have gone 100 times. Now, due to deformation of shapes, it maybe goes up to 50 times, and then that extra part is not going. So, I'm working on that so that with the help of polymers or with the help of cyclodextrin, with the help of uh, uh, actually proteins, or with the help of lipids, we are designing the aggregation. I mean, morphologically designed aggregators. Like maybe I can change the aggregation, maybe in a spherical one, maybe in a rod-shaped one, maybe lamellar kind of one, maybe it's a vesicular kind of thing. So by that designing of the morphology, we can also trigger the target specific ratiometric sensing by AI gene probes in a different level. So this is another next level of research, okay, in this field actually. Okay, so these are some well-known strategies for ratiometric AI gene probes. Okay, so now we are working. Now we will be showing some good examples where people have done very good detection of biological molecules and imaging of cancerous cells and all this stuff. So what happens here? You see this HTPQA. This is a molecule where the HTPQ, this OH, is hydroxyl group is converted to HPOO, PO4, PO4 minus group. Now, when its phosphate group is there, the whole molecule becomes water soluble due to presence of phosphate group, and the emission is not there. But due to this presence of this phosphate, what happens? It can target alkaline phosphatase. So when an alkaline phosphatase actually stays at the membrane of the cell. So what happens when it reacts or binds with alkylous phosphate? This O becomes free. This oxygen becomes free and goes takes up one hydrogen and put this hydroxyl group is there, and this becomes very fluorescent. And you can see this is a red fluorescent, red fluorescent molecule, and it gets deposited at the membrane, because membrane, the alkaline phosphate is in the membrane, and that's why the imaging of the membrane becomes very easy. This is a beautiful example where the biological enzymes are getting detected at the membrane. Okay, this is another example. Here lies here here this AIE lyso 1. This is the kind of structure you have, is designed to detect lysosomal esterase activity in live cells, and it also helps track lysosome movement. What makes this probe special that it combines two powerful features here: aggregation induced emission and also ESIP. So what happens? So it specifically targets first lysosomes and does not suffer from self-quenching, because it has a aggregation induced emission part, AIE part, and also the Stokes shift is very large. Just when I say Stokes shift, means the emission gets red shifted. Emission gets red shifted means from green to red, or maybe blue to green. Then what happens? This the good photo stability. This due to larger Stokes shift, you get a very good response. So what's really cool in this design is that the simplicity. Unlike many traditional AI probes that need to be very water soluble to keep background noise low, but here it's not like that. It works better by forming aggregates, which actually enhance the ESIPT emission. Okay, so here this is a kind of a very specific example where AI and ESIPT combines together to give you a fantastic ratiometric probe, which can bind with the lysosomal esterase, and it can sense lysosomal esterase in the live cell itself. So, okay, another one. It's called biothiol detection. Our cells are full with biothiols. So this is a kind of structure of the molecule. Now this molecule, what can do? It can bind with the glutathione. Glutathione we have in our system. Now, to actually, I am seeing the different celebrities and all these personalities. They are taking glutathione in saline to keep themselves young forever. So whatever normal, their normal cell has the GSH, they are not happy with it. They are putting additional GSH in their system. So to sense that GSH or glutathione, this molecule acts as I mean, really fine. So this is the absorption spectra, this is the absorption spectra, and this is the emission spectra. You can see when this TPE molecule, a TPE PPP molecule interacts with this GSH, it gives a clear-cut rate shift of the absorption happens, and also the emission also gets rate shift. So this, from the emission, goes from green to basically red. So this is a beautiful example, and this particular molecule can actually sense biothiols within your cells. And you can see this is the intracellular biothiol detection in HeLa cell using this molecule. Okay, so another one is that lysosomal pH. Here this molecule actually can, within this silica format, this molecule can sense lysosomal pH. So when this acidic pH, this fret is on, and you can see the green emission turns red here. Okay, this is also kind of ratiometric imaging of tumor reactive oxygen species. Um and here this is a very important, very good paper. This I like this paper. I mean, I'm working very similar to this actually. So what happens? They form with they have a molecule, and what they do first, they form a kind of gold anorod and polymer. This is called block copolymer. This is called pluronic F127. So F127 gold anorod and the molecule together, they put a composite like structure, and they basically can sense this temperature rising in the cell, and this is fantastic. So at low temperature, uh, low temperature, this emission, I mean, the green emission is getting higher and higher. So you can get a fantastic the A3, B3, C3, and D3. You can see the images are really good, getting really good here. Okay, so let's end this talk. So what are the take-home messages? Take-home message is scalable synthesis needed. So you can see most ratiometric AI gen probes are now complex and really hard to produce in bulk or simpler way. So we need high synthesis methods. So it's the way we are doing. I mean, all the proof of concept we have actually got past that. Now we have to actually synthesize. We need to scale up the synthesis, and we need to go for this kind of good AI probes which can image cells and biomolecules in the living cell. And you can see the rhodamine, fluorescein, nile red, they are very much available in market, but this kind of more efficient samples are not available, so we have to make them available pretty quickly. And boosting sensitivity, of course current probes are limited, have limited detection sensitivity. New designs with stronger amplifier signal response are needed, and expanding detection. And I mean we need, I mean for for a single fluorescent molecule, of course, we are limited to a certain wavelength region. Now, when we are doing this composite AI composite probes and all, we are actually covering a huge wavelength region, like from 480 to 650 or something. So this is very much important thing. And in vivo and theranostic potential, obviously probes are better, need better performance in vivo. Actually, due to this aggregation, uh, getting those probes out of the system, that's a problematic thing. So we need a like maybe a composite with the PEG or composite with the silica may increase the therapeutic functions like photothermal or photodynamic therapy. And of course shift to NIR or nanocomposite, shift to NIR, this is what most people are doing, because we don't want to irradiate our cells by normal light. Rather, NIR light, which is is of much less energy and which are less harmful for our cells. So, okay, so that's thank you very much for listening. I'm ready to take any questions. Hello, hello,
Yes, sir. Yes. And
Hello.
yeah.
yes,
Any questions, please?
participant can unmute themselves to ask any query.
हाँ जी सर, नमस्कार।
नमस्कार.
हाँ सर, ये अगर प्रो देखिएगा आप, ये मॉलिक्यूल सारे सर, इसमें बहुत सारे बेंजीन रिंग्स है, राइट? एंड दैट आर
Yes,
हाइड्रोफोबिक
yes.
एंड दैट आर यूजुअली टॉक्सिक। तो मुझे एक चीज जानना था, अभी फिलहाल मार्केट में इज देयर एनी प्रूफ दैट, जैसे कि हम रेडियो इमेजिंग करते हैं और कैंसर डिटेक्ट कर सकते हैं, या कुछ भी इमेजिंग करके किडनी खराब है, ठीक है, पता लगाते हैं, तो इज देयर इन
हाँ.
मार्केट एनी प्रूफ that molecule that is available in the market from the AIE Gen Pro? Can you please share?
या सो बेसिकली रेडियो फ्रिक्वेंसी के लिए तो अभी शायद मॉलिक्यूल्स कुछ जो कन्वेंशनल मॉलिक्यूल है वही है अभी तक। इसको रेडियो फ्रिक्वेंसी में मतलब व्हाट इज द वेवलेंथ रीजन, जो वेवलेंथ रीजन आप बोल रहे हैं वहां तक अभी तक शायद हम लेके जा नहीं पाए। हाँ, बेंजीन रिंग है आप जो बोल रहे हैं वो सही है कि टॉक्सिसिटी है, इसलिए तो हम कॉम्पोजिट बना रहे हैं। क्योंकि जो गोल्ड नैनो पार्टिकल, ये ऑलरेडी प्रूव हो चुका है, गोल्ड या सिल्वर नैनो पार्टिकल अगर आप डायरेक्ट सेल में डालेंगे तो उसका टॉक्सिसिटी जितना होगा, इफ यू कोट देम विथ सिलिका और इफ यू कोट देम विथ TUS और आई मीन सिलिका और समथिंग पॉलीमर और समथिंग, देन उसका टॉक्सिसिटी बहुत कम हो जाता है। तो सिमिलर टू दिस, if you can make a composite with this kind of molecules, because they are also kind of nanoparticles, they are not a single molecule, they are basically nanoparticles, and they have more than 30-40 nanometer, the size is more than 30-40 nanometer, in some cases almost in the micrometer region. So if you coat themselves or make a composite, then this toxicity level can be reduced, drastically.
सर आप ये जो मॉलिक्यूल्स है एआई जेन, आप कुछ बनाए हैं? जैसे कि मान लीजिए जितने सारे आपने
Yes,
दिखाया,
yes, yes. यस
जैसे कि
हाँ
हाँ,
जो
4
हाँ
बेंजीन
जैसे
रहता तो कुछ, या प्लीज प्लीज सर, कैन यू
हाँ
शो अस
तो
आल्सो
okay
what you have
just a minute
prepared?
that,
Please show us that one. Yeah,
okay
which
just a minute
one you have prepared, please? Yeah.
okay just a minute I can you can see my this right.
Yes, sir.
Okay, so here we what we did, we have this kind of molecule. You can see there are three benzene rings are there. Okay, so this molecule we did a kind of I mean we will not say composite, yeah, mixed aggregates, triblock copolymer. This is P123 and this is F127. So when we did
सर थोड़ा
this,
स्ट्रक्चर
so
दिखाएंगे
we
नीचे
have
प्लीज,
initially
आपका नीचे, सॉरी सर,
uh,
स्ट्रक्चर नीचे होगा शायद आपका पेपर में, थोड़ा दिखाएंगे प्लीज, कैन यू शो? नीचे तो स्ट्रक्चर होगा जरूर आपका, ये
uh,
तो थोड़ा सा बॉल स्टिक मॉडल हो जा रहा है तो समझ में नहीं आ रहा है कौन सा फंक्शनल ग्रुप है, आई
एक
कैन
मिनट
सी इट क्लियरली, या नीचे होगा स्ट्रक्चर उसका।
एक मिनट सपोर्टिंग में होगा या दिस इज द
या दिस वन
स्ट्रक्चर कैन यू
सपोर्ट,
सी या कैन यू सी द स्ट्रक्चर
हाँ या यस सर, या
yeah this is the structure of the molecule okay so
हाँ
the beautiful the beauty of this study is that when you have two different molecule two different block copolymers you have two different kind of structure this is in presence of block copolymer P123 you have a spherical structure in F127 you have a rod like structure and due to with this we done this FLIM to understand the mechanism of formation. And what we did the study on HeLa cells. What happens that the rod-like structures can easily penetrate through the cell membranes to enlight the lipid droplets. But they are in spherical shape, they cannot penetrate because they are bigger in size. They cannot penetrate the cell membrane and they cannot, lighten up the lipid droplets.
सर ये मॉलिक्यूल आपने बनाया था या खरीदा था?
ये बनाया हुआ है. This is
या
this is
इज देयर
actually
एनी
given. No,
मॉलिक्यूल?
no.
या
This I did not make this. Let me tell you. This is made by Professor Anil Kumar, IIT Bombay. So he has he's a student Ratika Maini. She has synthesized this actually.
अच्छा सर, सर मैं आपको एक मेल ड्रॉप करूंगा, हाँ प्लीज रिप्लाई करिएगा।
Yes, sure. Yes,
ओके
sure.
ठीक
Of
है,
course.
थैंक यू।
Of course. Yes, anyone?
Any questions, please? Any questions from the audience?
I think there is no
There are no more
question.
questions, Dr. Akshay. Thank you very much
Yes.
for your dynamic and
Thank you
clear
very much.
talk on molecular aggregates for biosensing and imaging.
Now I'm
Explanation
stopping
of
this.
application-induced emission mechanisms and their tunability for biological environment provided valuable insight into their growing potential in real-time diagnostics and biomedical imaging. Thank you very much. Now I will
Thank
ask
you very
Dr.
much.
to present a token of gratitude as a virtual memento, as a gesture of appreciation to our Dr. Akshay.
Thank you very much. Thank you very much.
Dear sir, please accept as a guest.
Thank you, sir.
Yes, sir.
Thank you, sir. Okay, sir.
Yes. Thank you so much, sir. Sir, we are kindly request you to kindly uh, ask the Pramanik sir to
Yes,
join.
yes, sir.
Yes.
I'll call him. I'll call
Yeah,
him.
yes,
I'll
sir.
call him.
Yes.
Yes.
Yes, sir.
Thank
Thank
you.
you, sir.
Thank you, sir.
आपको बोल दिया
that light beats the
Hello, Dr. Pramanik. Dr. Pramanik, unmute yourself. Are you able to hear me?
Sir, Pramanik sir has joined. Shortly he will be
Okay,
with
shall
us.
I start?
Pramanik sir?
Can you hear me, Pramanik sir? So we are moving towards our final session of the day. Our final session day will be delivered by Dr. Smriti Moy Pramanik, a leading researcher from University of Calcutta. Dr. Pramanik did his bachelor's, master's and PhD from Jadavpur University. Before joining University of Calcutta, he was a postdoctoral fellow at Frontier Institute for Biomolecular Engineering Research, Konan University, Japan for 6 years. His current research interest focuses on effect of homogeneous and heterogeneous crowding on the behavior of biomolecules, effect of intracellular interfaces on the behavior of biomolecules, that is membrane biophysics, protein nucleic acid interaction, that is central dogma of gene expression, targeted cell-specific drug delivery. He will be delivering a session on thermodynamic of nucleic acid structure formation. Sir, we request you to begin your session.
Yeah, so am I audible?
Yes, yes, you are audible, sir.
Okay. So thank you for the introduction, Dr. Ahuja. I would like to. So have you finished that your introductory topic?
Yes, yes, sir, we have finished. You kindly make the full screen.
Oh, okay. So is it my screen is not visible?
Sir, make it in a slide, the PPT.
Slideshow.
Yes, sir.
Okay. Now is it fine? Can you see the full screen?
Yes, sir, we can see, but screen is small. If you can make it big, then it's okay. Otherwise, you can proceed.
Okay. So I say I could make it a full screen. So let's see.
You can proceed, sir.
Yeah, I shared that full screen. Yeah, now is it fine?
Yes, sir, it's fine. It's good. Thank you.
Okay. Now we can start.
Yes, yes, you can start, sir. Thank you.
So first of all, I really thank Dr. Ahuja for the brief introduction that you had given on me, and I'd like to thank Dr. Umesh for the invitation to give a talk in this faculty development program, and all the other co-convener and the volunteers which were involved. So yeah, to make it possible. Okay, so I slightly changed my title of my talk. So mm, my talk is based on the brief journey into the world of nucleic acid chemistry. Okay, instead of just thermodynamics, I thought maybe uh, just thermodynamics maybe just for the physical chemist. But of course, as I'm trained physical chemist, so this journey will be mostly through the physical chemist point of view. So first of all, I'd like to thank my students and the financial support that I have received from the Ben's Search and the faculty district faculty inspire program. Okay, and to prepare this presentation, I took help from these 4 books. That molecular cell biology and nucleic acid and the physical chemistry. Okay. And some journal references which are cited in appropriate places. Anyway, as you know that the shells that the beginning of life which are of 2 types. Okay, the cells are of 2 types: prokaryotic cells and eukaryotic cells. Okay, so and the difference is that between prokaryotic and eukaryotic cells is that the prokaryotic cells where the genetic material, that's the DNA, uh, is not separated from the cytoplasm matrix. On the other hand, in the eukaryotic cell, that genetic material DNA is separated by a well-defined nuclear membrane. Okay. And the molecules, which are the fundamentals about the building blocks of the cells. Okay. Anyway, in eukaryotic cells, so for the advanced life form, so these are made up of eukaryotic cells. So in the eukaryotic cells, that I have told you that the nucleus, okay, that is clearly visible in the nucleus, so that the nuclear core. So these
Can
pores.
you speak little louder, as the audience are not able to hear you clearly?
Oh, sorry. Oh, so they cannot hear me?
Yes, we can hear you, sir, but your voice is very low. If you
Very
can,
low. Oh, okay.
if you can increase the
Oh,
volume of your mic, or
so now is it okay?
yes, yes, sir.
See if I hold.
Now it's
Now
better.
is it okay? Okay, okay. So okay, it's okay. So sorry for that
Okay.
inconvenience. So now I hold like this, so maybe it will be more like I hope. And anyway, so so that as I had mentioned earlier, so that nucleus where the genetic materials stored within eukaryotic cells, and it's very completely separated from the cytoplasm matrix. Okay, so in the cytoplasm matrix where other organelles, so for example, mitochondria and Golgi apparatus, etc. Those are. So it is important to mention here that the genetic similarities between us as a modern human being and some with some other life forms. Okay, so we have significant similar genetic similarities. Okay, so percentage of similarity that you can see in this slide. Okay, so possibly which made to the conclusion that maybe we all evolved from a common single cell ancestor. In fact, so that genetic similarities between mankind, that 99% of the nucleotide sequence is similar or the common to all mankind. Okay? And the remaining only 0.1% is different for each individual. And that actually regulates our life cycle. For example, so instead of that GC base pairing, if we alter to that AT, then certain people, as you know, they are very vulnerable to alcohol, and some people are resistant to alcohol. So in that case, so those who are resistant, so they have GC base pairs. On the other hand, those who easily got drunk, so they have that AT base pairs. Okay, just single image. Okay, so I start firstly with the importance of the nucleic acids in cell. Okay, so that the central dogma of gene expression is basically two-step process. So in the first step of reactions, so from DNA to synthesis of RNA. So by the help of RNA polymerase enzyme. Okay, that will perform that reaction or the transformation. Okay, in the next step, which is known as translation, so from where RNA to protein synthesis. Okay. So this is the two step, as I said. So and consequently, the nucleic acid structures, so that means both DNA and RNA, they are very important part of our living cells, living systems. So now, briefly, I'd like to mention that if we want to control the gene expression process, either we can uh, we can interfere in the translation step or in the transcription step. And this transcription, it is basically three-step reactions. So first is the initial cell step, where that RNA polymerase bind to the start codon of the start site of the promoter sequence, and then it is it unwind DNA and RNA synthesis takes place. And by doing so, there may be 8 to 10 base pairs of RNA hybrid structure formed within this transcription bubble. Okay, and then finally that polymerase reaches to the stop site, and the RNA, pre-messenger RNA is released, polymerase also released, and then this pre-messenger RNA processed further to produce the mature messenger RNA. Okay, and the translation reactions is that where that transfer RNA and ribosome attached to that messenger RNA, and then transfer RNA is also attached, and then this translation machinery moves along the messenger RNA, and then finally we get a polypeptide chain, and this polypeptide chain correctly folded, maybe in the Golgi apparatus, to get a correctly folded protein. And inside cell, the DNA can make its own copy. And so by the reaction known as the self-replication of DNA. Okay, by helicase and helicase enzyme and the DNA polymerase. So these are the key things. Of course, other factors also there. So, but main important players are the helicase enzyme and the DNA polymerase. So by this DNA can self-replication process, DNA can make its own copy. And also by a reaction known as the reverse transcription, where the reverse transcriptase enzyme make a copy of DNA from RNA molecule. So those are the two reactions. So inside cell, so DNA can be synthesized, and in the case of RNA, that RNA polymerase ribozymes are able to replicate RNA. Okay, they can make their own copy, and which leads to the RNA hypothesis that self-replicating RNA molecules that were the precursor of all current life. This is the RNA molecules. That is some group belief that so every RNA was the first molecule, which leads to complex life. Okay, anyway, and the reverse translation from the protein to RNA is not known. Okay. So DNA molecules or the genetic material DNA that is packed inside the nucleus. So it's pretty very long. Okay. So if we roughly calculate the length of total DNA present in our body, so roughly we can make one round trip to the interstellar space where the Voyager 1 spacecraft presently residing. Okay, so you can imagine. So how big is the DNA? So that are such DNA molecules inside our living system, inside cell are packed in super compact form that through that with some protein. So the DNA can form complex, and then they assemble together and forms the chromosome. Okay, so the chromatin structures are of two types: the heterochromatin state and the euchromatin state. In In the heterochromatic state, the proteins and DNA, they are very tightly bound for. On the other hand, that euchromatic state, that the DNA and protein are loosely bound. Okay. And one important thing is that the heterochromatin state is inactive in the gene expression. On the other hand, euchromatin state is active in the gene expression. So this chromatin structure is very important for the cell life, the cell life cycle. Now I would like to discuss about the nucleic acid structure and properties. So, so DNA structure, double helical structures. So the journey to establish these structures started in the year 1866, and after several refinement of the several discovery, so in the year 1953 only we get the beautiful double helical structures of a DNA molecule by Watson and Crick. Okay, from this beautiful X-ray crystallographic figure taken by the Franklin Rosen group. And they said, Watson and Crick said that the double helix structure is produced by A and GC base pair. That is very specific. And this specific arrangement means the specific arrangement of A and AT and GC, they can store the genetic information. So these are the 5 nucleobases. So for the DNA, so adenine, guanine, cytosine, and thymine. And in the case of RNA, instead of thymine, so there exists uracil. And this, when these nucleobases attach to the sugars, so for example, in the case of DNA, so it attaches with the deoxyribose sugar, the deoxyribonucleoside, and when that the deoxyribonucleoside attaches with phosphate backbone, so they are known as deoxyribonucleotide. And 2 kinds of bases we can classify: the purine bases are the adenine and guanine bases, and then the purine bases. And the pyrimidine bases are the cytosine, thymine, and uracil. Uracil in the case of R. And so this phosphodiester bond formations so leads to the formation of the chain of nucleobases. They attach with each other, and then so another strand opposite in the opposite directions. So from 5' to 3' in the opposite directions they run, and they form this canonical Watson-Crick type duplex structure between the AT and GC. AT forms the 2 hydrogen bonds, and on the other hand, GC can form 3 hydrogen bonds and pair with each other. Okay, so by doing so, so they forms major group side and the minor group side. Okay, so these groups run along the helix, the major group and the minor group. And these groups are extremely important for the DNA structure and stability. So in the case of B-form DNA, that is a canonical duplex structure, so there exists a spine of hydration that is run along the minor group. And this spine of hydration is thought really that they prevent the BDNA structures and prevents its transition from B to A. In fact, in less hydrated conditions, so for the less solvents, so the BDNA often there often exists a transition from B to A form. Also, there exists some non-canonical base pairing in DNA. So initially, these were thought these were proposed by chemists, and these were not considered important for the biological aspects. But later, it was proved that this kind of non-canonical base pairs can also exist in vivo conditions. So, for example, that TA and prototype cytosine and guanine, they can form each of them between them and the pair, and they can form parallel kind of duplex, not antiparallel that I have mentioned earlier. That antiparallel duplex, but the antiparallel duplex. But here, so the strands run in the same direction. Okay, so the parallel duplex, and moreover, so they can form triple helical structures by pairing three nuclear bases, for example, prototypic cytosine, guanine, and cytosine. And also, four-stranded structures are also proposed, for example, that G-quad duplex means and I-motif. Okay, so G-quad duplex structure formations involved, so that four guanine bases stack in a same plane, and they are paired by histine hydrogen bonding between them. And in the presence of symmetry metal ion, so these G-quadrates are stacked on each other to form these kind of four-stranded structures. And cytosine and prototypic cytosine, they also form non-canonical this kind of pairing between them, and these kind of four-stranded structures of I-motifs can be formed. And this kind of non-canonical structure formation, for example, the formation of G-quad duplex, they are shown to regulate biological, important biological reactions. For example, telomere replications can be inhibited by the formation of G-quad duplex at the telomere. Okay, so this was already shown, and the transcription and also translations, they can also be inhibited or regulated sometimes. So by the formation of this kind of non-canonical structure. So these are following these kind of publications. So in vitro, these are all in vitro. And also there exists some mismatch based pair. Mismatch, so AT instead of AT and GC, so AA mismatch or CCGG or TT mismatch. This kind of mismatch based pairs formations are also reported. And this kind of mismatch based pairing can occur during the replication or due to the niche on incorporation of the base, nuclear bases. So this kind of, for example, also to the TT mismatch there. And also this can lead to non-duplex structures. For example, in loop or etc. They can form instead of the duplex. And they can lead to the this kind of triplet repeats that you can see. So this kind of mismatch can lead to several diseases, for example, Fragile X syndrome, Huntington disease, etc. So this kind of mismatch is extremely important. Okay, so just immediately I show something that how the misincorporation of bases can occur during the replication process. That is, so by replication means that when DNA is making its own copy, and by some mutagenic chemicals. Okay, so some mutagenic chemicals, they can also lead to this kind of mismatch pairing, and where the guanine can be converted in hydroxyguanine, or some ionizing radiations which can lead from adenine to 2-hydroxyadenine, and spontaneous deamination. An example is that from 5-methyl citation to thiamine. Okay, this kind of conversions. Okay. And for example, that the DNA methylation or hydroxymethylation, so they are shown to stabilize the DNA secondary structures. Okay, the thermal stability of the thermodynamic stability was increased in the if we convert cytosine to 5-methyl cytosine. And also it was shown that 5-methyl cytosine, that conversion of 5-methyl cytosine can refresh the transcription process. I'm stuck. Oops. I'm sorry. Some problem. Okay. Okay. So, and just sorry for the inconvenience. Okay, and also that sugar conformations that deoxyribose sugars are in the C2 prime C2 prime endo sugar conformation. On the other hand, ribose sugar prefers the C3 prime endo sugar conformation, and these sugar conformations actually determines the nucleic acid structure. The sugar property determine the one final nucleic acid structure that usually the DNA prefers that the B form structure due to this C2 prime endosomal conformation. On the other hand, RNA duplex prefers the A conformations due to this C3 prime endosugar sugar pathway. Okay. Oh, so metalloids usually played its part for the structure and stability of nucleic acid structures. Okay, so so for example, this G quartet formations, as I mentioned earlier, that central metalloid is extremely important to form this G tetrad. Okay, so for it can help to arrange four guanine in the same plane. So anyway, so that DNA having this kind of BDNA, ADNA, and ZDNA structures. So and the important difference between these two structures is that A form structures is thick and compressed along the helix axis. Okay? On the other hand, Z is elongated and thin, and B is intermediate in between them. Okay, so now the question is that the in-cell conditions or in vivo conditions. So the DNA structure is just a boring canonical duplex structure or not. Okay, so to characterize the DNA structure and stability, so some robust methods I'd like to discuss. One is the cycloidal dihydrogen spectroscopy of the CT spectroscopy to address the structure of nucleic acid secondary structure. That CD is nothing but the difference in left-handed and right-handed supplement slides. And so different form of different structures, and you can see from the table they have signature the positive or negative peak. And the evaluating studies, and also that absorption spectroscopy implies structures. So to study the nucleic acid structure stability. That nucleic acid shows the maximum absorbance in the EF region around 260, something like that region, due to the presence of delocalized electrons, nucleobases. Okay. And when this nucleobases become, when they are structured state, when they are stacked with each other and paired with each other, complementary bases, so their absorbance is less. But when you melt them or when you apply some external stimuli, for example, the temperature, if you increase the temperature, the experience associated, then the absorbance increases around the lambda max, and you get this kind of melting curve. Okay, so that if you plot normalize absorbance versus temperature. Okay, this kind of thing. This is because that that in the case of stacked bases and paired bases, that the transition dipole and induced dipole, they are of a different range. On the other hand, in the collinear basis, when you are building structures, so bases become almost collinear. So in that case, so the transition dipole and the induced dipole set in the same range. Okay. So if your dipole is very high, so you get high absorbance at the lambda values when you're building structure. Okay, next is I'd like to discuss about the thermodynamics of nucleic acid structure formation. So why we need to study this kind of thermodynamics? So answer is that this kind of quantitative is a quantitative analysis approach. Okay, quantitative analysis. So we can make a database, and based on database, so we can build functional models for different applications. For example, drug design, sensing, molecular switch, etc. We can apply in nucleic acids in this field. And these are the 5 factors which can determine or affect the structure and stability of nucleic acids, which are number 1 is a hydrogen bonding between nucleic acids. So, in the case of canonical stability and okay, and stacking. Stacking means that stacking interaction. Stacking means stacking between 2 adjacent nucleic acids. Okay, within the same stack. And the conformational entropy and this hydration of this hydration of the solution. So, so in the case of nucleic acids, living systems also is the hydration. And the counter ion condensation, because the phosphates, as you see, that phosphate backbone, if you can remember, the phosphate backbone and helix. So, if you are 2 or more than 2 strands pairing with each other, so there must be electrostatic repulsion. In order to counter that, you need counter ions. So these are 5 factors: stacking, conformation, hydrogen bonding, summation of the product, and cation, counter ion condensation. So these factors, 5 factors, play important role, crucial. But individually, we cannot experimentally, we cannot trace or can estimate each of the factors. Okay. So in the we measure only the overall process. Okay. And important to mention that except that the free energy change of the conformations, all other are favorable for the nucleic acid structure. As you can know, that gives free energy is a function of temperature and pressure. So at constant pressure, we can estimate the enthalpy change and the entropy, which is usual. Usual means very common, most frequent in the liquids. And on the other hand, of course, there are few, but the experimental setup itself is very challenging because at constant temperature we have to vary the pressure. Okay, so you need a very special kind of apparatus, sample holder to increase the pressure. Okay. So then, by utilizing Clausius-Graf-Pyron equation, you can estimate the volumetric change upon the nucleic acid structure formation. But this is possible, and there are quite a few letters to create this the volumetric change. Okay, so I've already discussed about this melting curve. So you get from the structured state to unstructured state when increasing the temperature, and from there you can calculate the fraction of structured state. We can calculate, right, for fraction of the structured state by this ratio, right, from this relative amount. So if we now plot the fraction of structured state versus temperature or the inverse temperature, so we can estimate or evaluate the melting temperature that is inverse. Okay. And we can, I'm not going into detail in this kind of derivations or something like that. So we just see this equation 3. So this is for the Hancock equation. So we can feed here that from the melting temperature. So from a melting temperature, so from the slope, if we can slope, we can feed in equation 3. So we can estimate the Hancock enthalpy. And also, so by utilizing that equation 6 or 9, so if we plot melting temperature inverse versus log CT, so then we can from this slope and intercept, we can estimate those thermodynamic parameters, that enthalpy change and entropy change. But the condition for this kind of treatment is that uh, the DNA or the RNA that we are dealing with, this would go through a two-state transition. Okay, so non-two-state transitions, so we cannot apply these kind of models to estimate thermodynamic parameters, and we can judge whether some process is two-state, going through a two-state or non-two-state. So just we, for example, in the melting, so um, and annealing. We have to perform annealing. Annealing means so high temperature to low temperature. So if the two paths are following identically same, so then this is a proof that this is a two-state process. On the other hand, if there are some hysteresis the uh, within the curve, so you can say this is a non-two-state, and in that case, we cannot apply those models to estimate thermodynamic parameters. And also by CD spectroscopy, so that if we take the CD spectra from low temperature to high temperature, so if it is a two-state process, so there must be isodipole point, but that is equilibrium. So isodipole point should be there in CD spectra. So the anyway, so another thing is that we can estimate thermodynamic parameters by differential scaling calorimeter. So of course, so that implementing studies are very robust and they often you need less sample, but it suffers from this kind of two-state, non-two-state process or sometimes assumption. But in differential scaling calorimetry, so you can estimate exact thermodynamic parameters. So here, so you have to just take sample and one reference, and then you hit from low to high temperature. And from this kind of equation, you can estimate thermodynamic parameters. Okay. So if you plot CPXS versus temperature and CPXS, you can estimate the enthalpy change and entropy change. So CPXS divided by temperature versus temperature. If you plot that area under the curve, will give you the entropy change. And this between the difference between the folded and folded state will give you the delta CP. Okay, so now I'd like to discuss about the cell mimicking conditions. So often we are doing experiment in the laboratory. The conditions are very dilute. Okay, so it is very far from the in vivo shell conditions, where the condition is very complex and very high concentrations of water molecules also they are present okay, so that okay, in order to mimic the shell like conditions, so for example, the molecular crowding conditions composed induced by some other proteins from other molecules, different molecules, and also the confined space. There exists confined space, for example, the nucleus and other organelles, mitochondria. So they can induce some confined space and also heterogeneous surfaces, for example, that biomembrane, nuclear membrane, or the cell membrane, or the membrane of the organelles. So those are heterogeneous surfaces. Okay, we need to move all these things. So in order to do so some co-solutes introduced co-solutes, sometimes introduce co-solutes to mimic the molecular crowding induced by other molecules and this confined space. So, for example, we can use reverse micelles, etc., to make compartmentalized space to mimic the confinement. And we can use the liposomal surface to mimic that biomembrane heterogeneous surface. Okay, so from these nucleic acid structure formations that if you take co-solutes and cations and so in the solutions, so by this kind of treatment by utilization tool, we can estimate that number of water molecules released or taken up in the structure, nucleic acid structure. So if that in this equation, if you plot that log the observed versus log of water activity, and if it is just linear, so you can estimate the slope from the slope that the number of water molecules involved in this process. Okay, so that eta minus delta index is positive if the number of water molecules are taken up during the structure. On the other hand, if minus delta index is negative, if you estimate it is negative, then the water molecules are released during the structure. I'll just give you one example is that is for the Watson-Crick base pair that usually it leads to the positive slopes. Okay, positive slopes, that means water molecules are taken up. On the other hand, that Hooke's base pairs, that non-canonical kind of base, but the non-canonical kind of base pairing show that a slope often get in the negative slope. So that means so that water molecules are released during the non-canonical base pair formation. So thermodynamics is very powerful tool. We can by some simple thermodynamic treatment, we can say that water molecules are released or taken out in the base pair formation. Okay. Okay, so yeah, so okay, so I just quickly show one of my work that I did with we did with the DNA and formations that molecular carbon effect on this DNA and structure formations. So I had already mentioned that during the transcription process, maybe 7 to 10 base of DNA structures are formed, and also they occur in the in vivo during the retrovirus replication process. These kind of DNA RNA structures are formed. So that molecular crowding conditions can conclusion of that study was that molecular crowding condition can extract not only the information of hydration but also kind of conformation of nucleic acid complexes, and that we only uh, study by means of thermodynamics. And as you can remember that heterochromatin and euchromatin state, I have discussed that briefly that heterochromatin is a tightly packed form of DNA and protein, and euchromatin is a loosely bound form of DNA and protein. So that the histone proteins are actually histone protein. Right? So the proteins that compensate. And our study revealed that not only molecular crowding, but the histopeptide, that is peptide, and structural polymorphism in humans. And obviously, which can alter the structure. And that G-rich, the telomeric, human telomeric DNA, that is the part of the telomeric DNA sequence, so the G-rich and this right hand side, this series DNA sequence. And in vitro, they can form G-quad duplex and I-motive structures, okay, individually. But however, if we mix in equimolar ratio, the series and series sequence, they are complementary each other. In dilute solution, they form duplex. Okay. But however, the nuclear confined space-like conditions, it is by, for example, reverse micelles, so significant fractions of non-canonical structures were formed that we observed. Okay. And the heterogeneous surface that I have observed by utilizing, for example, liposome, that this kind of non-canonical G-quad duplex structures were destabilized when they are embedded into the heterogeneous liposome surface or microscopic surface, say. And this kind of destabilizations can actually affect the transcription process. So, for example, initially when the duplex is formed, the transcription that RNA 57 RNA polymerase cannot move. Okay, so when the kind of duplex stop, but when the duplex is stabilized, this is polylinear, the transcription bubble running very smoothly, and we get a very high amount of transcription product, which can be seen in this figure. So this number 3 lane, okay, in figure B, number 3 lane, okay. So that amount of transcription, transcript increases, okay, in the presence of liposome. So direct proof that, yeah, so this kind of G-quad structure used for formation of facilitate the transcription process. And it concludes that the status of genomic DNA cannot be must be just canonical duplex. These consist of yeah, so the loop structure, triple helix, or G quadruplex or binary, and also significant properties. Okay, so thank you for your attention. So now questions, comments, feel free to answer. Any questions from the audience? Any questions from the audience?
Sir, I think the audience don't have any questions. They think that it was a very informative session. So,
Okay. Okay. So yeah. So yeah. If not questions.
okay, sir.
Okay.
Thank you very much, Dr. Pramanik, for that highly
Oh,
technical yet
okay.
accessible talk. Your insights into the thermodynamics of nucleic acid structure formation provided deep understanding of the fundamental principles that govern molecular stability and interactions, highly relevant to current advances in biomedical. Wait, thank you very much. Now I would request, I think Dr. Ashok has some questions. He has raised his hand.
Oh, open in a chat.
Gaurav sir, please unmute Dr. Ashok.
हाँ जी सर, नमस्कार। हेलो
Pramanik
Hello.
sir.
Yes.
हेलो।
Hello. Yeah.
हाँ सर,
Hello.
आवाज आ रहा है सर? आवाज आ रहा है सर?
Yes. 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 I can hear you.
हाँ सर, थैंक यू सर, थैंक यू, थैंक यू सर। माइक खुला नहीं था ना, इसीलिए मैं परमिशन नहीं था ऑन म्यूट
No.
करने
No.
के
It's
लिए,
fine.
तो टाइम लगा। हाँ
Okay.
सर, सर आपने बहुत बेसिक और इंफॉर्मेटिव नॉलेज दिया, स्ट्रक्चर, हाइट बॉन्डिंग कैसे हो रहे हैं, क्या ड्रग्स के रिलेटिव। मगर सर मेरा क्वेश्चन ये है कि सर हम, आपने जो कुछ काम किए हैं तो वो थोड़ा प्रेजेंट करते बताते, लास्ट में बहुत कम बताया, तो इतना मतलब समझ में नहीं आ सका कि हम कैसे इसको अपने रिसर्च में डाल के आगे बढ़े। जैसे कि पिछले क्लास में हमें मॉलिक्यूलर इमेजिंग प्रूफ बताया गया, बहुत बढ़िया, बहुत अच्छे से बताया। तो हम इस मॉलिक्यूलर इमेजिंग प्रूफ और आपका जो टॉक है वो दोनों को कंबाइन करके कैसे रिसर्च कर सकें। मैं तो यही सोचा कि आपका जो है, या वेरी गुड कि ये न्यूक्लिक एसिड ड्रग थेरेपी है, एंड ये दैट इज द मॉलिक्यूलर इमेजिंग टेक्निक। तो दोनों को कंबाइन करो, कुछ मॉलिक्यूल सोचो। तो मुझे आप बताइए, आप क्या सजेस्ट करें इसमें, प्लीज।
Okay. So, okay, I understand your question. So, yeah. So, uh, first of all, that I didn't mention my research in detail. Okay. So, means for example, that detail results or something that I didn't discuss. Okay. So, I thought maybe this is a faculty development program. So, I just give some brief idea. Okay. So, from that perspective, I just omitted the results. Okay. So, but yeah, you can combine those things and it will be a very interesting study. Yeah, so imaging, for example, AI agents or something that yeah, Dr. Rohit was talking about, right? For the imaging purpose, AI agents, right? Yeah, so you can utilize in DNA structures also those kind of AI genes. So to see or to visualize the structural changes within the nucleic acids.
सर मुझे बताइए कि मैं अगर एडेनाइन के साथ ये एआईए चेन को टैग कर दिया, राइट,
Yes.
टैग कर दिया, और जब डीएनए का बॉन्ड बनने लगेगा, एटी बॉन्ड बना मान लीजिए, तो इज देयर एनी हिंड्रेंस कि ऐसे ऐसे करने से क्या होगा क्या नहीं होगा, वी डोंट नो, राइट। तो ये तो
Yes.
कॉन्जुगेशन बना जा सकता है और ट्राई किया जा सकता है। तो अगर डीएनए बना और
Mhm.
क्रोमोसोम बना तो वो तो ग्लो करेंगे ही करेंगे, क्योंकि उसके साथ
Fine.
तो फ्लोरो। हाँ,
Yes. Yes.
तो
Yes.
आप अगर कुछ दिखाते ना, बड़ा इंटरेस्टिंग लगता सर। मैं तो यही सोच रहा था कि आप डाटा एनालिसिस, क्योंकि सर हम तो टीचर हैं, पढ़ाते तो है सारे चीज, तो सारे चीज तो थोड़ा बहुत तो
No,
नॉलेज था।
yeah, so those kind of, so yeah, so there are many studies so that proves they can tag on the DNA, maybe 5' sometimes 3'. Yeah, so those are very expensive DNA sequence. Trust me, okay. So
नहीं सर,
the,
आपसे आपसे आइडिया तो मिला, और पिछले साल से आइडिया मिला, नॉलेज मिला, कंबाइन करके बढ़िया काम हो सकता है। कुछ भी जरूरत हो
हो
तो
सकता है,
मैं शायद
but
आपको
those
मैं
kind of,
जरूर जरूर मेल करूंगा, प्लीज रिप्लाई
oh,
करिएगा,
of
ये
course,
रिक्वेस्ट।
you are, please feel free to email me or
या,
something like
बहुत
that.
बढ़िया
If
नॉलेज
I
मिला सर।
if I can help anything, so I'll be more than happy
यस
to
सर,
do that.
योर हेल्प विल
But
बी
I
वेरी।
Yeah. So, but I can tell you one thing that if you are doing those kind of some attaching fluorophore with the DNA or something, so if you want to purchase, that will be very, very, very expensive.
नहीं सर,
You
मैं
can
बना
just
लेता हूँ सर। सर मैं बना
okay,
लेता हूँ, मैं पेप्टाइड बना लेता हूँ, तो एडी 9 बेस खरीद के बना लूँ ना, उसमें क्या।
okay. If you
हाँ
are
तो
comfortable with the synthesis of peptide, maybe.
हाँ
Yeah,
हाँ
I did
सर,
one.
हाँ
I
हाँ
did one time by myself, maybe 17 amino acid by coupling a mock. Okay, I did by myself. Oh, it's
हाँ
a
हाँ
very
सर,
good
हाँ सर, वो
and
कर
very
कर
time
लूंगा सर, वो
consuming.
कर लेंगे।
Very
कुछ
time
मगर आपका
consuming.
हेल्प जरूर लगेगा, आपका हेल्प
Okay,
जरूर लगेगा, मदद
okay,
चाहिए होगा सर। ठीक है
okay,
सर, थैंक यू सर। हाँ,
okay, okay.
नाइस टॉक सर।
Okay, thank you very much for listening.
So thanks for your
Any other
time.
question, please?
Dheeraj sir, you go ahead with your.
So now I request Dr. Yuvnesh to present a virtual memento to Dr. Pramanik uh, for his wonderful session as a token of gratitude.
Vikasji, please share.
I will request Dr. Vikas to kindly share the memento screen.
Huh.
Thank you.
Sir, thanks for your time and time for sharing the knowledge. So it was wonderful section. I hope the audience has enjoyed it a lot. And I
Thank you
hope
very
in
much.
future if you can
Thank you.
we can see more of your progress. Thanks a lot, sir. Thanks a lot for your time. Please accept
Okay,
the
okay. Thank you.
token as a gratitude.
Thank you very much. Thank you very much for the invitation, and I hope some information may be useful for some faculties. Okay. So
Okay, sir.
on this note, thank you very much.
Okay, sir.
Thank
Thanks.
thank
Thank you, sir. We'll get back to you soon in the coming
you. Okay.
episode.
Okay. Thank you. Yes, you can get back to me. Okay.
Okay,
Okay.
sir.
Mm, thank
So we move forward. Uh, this brings us to the close of day 5 of our faculty development program. We extend our heartfelt thanks to all our speakers and participants for making this day intellectually fulfilling. So that's all for today. Have a nice day. So you
Thank you,
all are
sir. See you.
to share, fill your feedback form that is being shared in the that has been shared in the chat box. So, Yogeshwar, is it okay?